shows of fun. Now the jingle hop has begun. Jingle bell, jingle bell, jingle bell rock. Jingle bells chiming, jingle bell time. Dancing and prancing in Jingle Bell Square. In the frosty air, what a bright time. It's the right time to rock the night away. Jingle bell time is a swell time to go gliding in a one-horse sleigh. Giddy up, jingle horse, pick up your feet. Jingle around the clock. Mix and a mingle in the jingling beat. That's the Jingle Bell Rock. What a bright time, it's the right time to rock the night away. Jingle bell time is a swell time to go gliding in a one-horse sleigh. Giddy up, jingle horse, pick up your feet. Jingle around the clock. Mix and a mingle in the jingling beat. That's the Jingle Bell, that's the Jingle Bell, that's the Jingle Bell
Dashing through the snow in a one-horse open sleigh. O'er the fields we go, laughing all the way. The bells on bobtail ring, they make our spirits bright. What fun it is to ride and sing a sleighing song tonight. Jingle bells, jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh. Jingle bells, jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh. A day or two ago, I thought I'd take a ride, and soon Miss Fanny Bright was seated by my side. The horse was lean and lank, misfortune seemed his lot. He got into a drifted bank, and we got upside. Jingle bells, jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh. Jingle bells, jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh. Now the ground is white, so go it while you're young. Take the girls tonight and sing the sleighing song. Just get a bobtail nag, 240 for his speed. Then hitch him to an open sleigh and crack, you'll take the lead. Oh, jingle bells, jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh. Jingle bells, jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh.
I don't want life for Christmas. There is just a thing I need. I don't care about the presents and the need a Christmas tree. I just want you for my own, more than you could ever know. Make my wish come true. All I want for Christmas, you. I don't want a lot for Christmas. There is just one thing I need. Don't care about the presents and the little Christmas tree. I don't need an Emma stocking there upon the fire.
could hold my head up high. And it's been a while since I first saw you. And it's been a while since I can stand on my own 2 feet again. And it's been a while since I could call you. And everything I can remember, how bad it all may seem, the consequences that are rendered, I stretch myself beyond my means. And it's been a while since I could see.
Welcome to the Neuralink Show and Tell. So we've got an amazing amount of new developments to share with you that I think are incredibly exciting, as well as tell you about the future of what we're planning to do here. It's now this is meant to be a technical podcast, sort of like I'm going to provide an overall summary, and then we're going to have a number of members of the Neuralink team come in and give a deep technical overview of the various areas. So so let me move forward with the overall summary. Now, some of the things I'm going to say are things if you've been following Neuralink, you've already heard before, but for a lot of people out there, they've no idea what Neuralink does, and so I will be a little bit repetitive of things you may already know, but that others do not. So, the overarching goal of Neuralink is to create ultimately a whole brain interface. So a generalized input-output device that, in the long term, literally could interface with every aspect of your brain, and in the short term, can interface with any given section of your brain and solve a tremendous number of things that cause debilitating issues for people. So. So our long term is I'll talk a little bit about our long term goal. It's going to sound a little esoteric, but it was actually the sort of my prime motivation, which was, what do we do about AI? Like, what do we do about artificial general intelligence? If we have digital superintelligence that's just much smarter than any human, how do we mitigate that risk? At a species level, how do we mitigate that risk? And then even in a benign scenario where the AI is very, very benevolent, then how do we even go along for the ride? How do we participate? And the conclusion, the thing that the biggest limitation in going along for the ride and in aligning AI, I think, is the bandwidth, the how quickly you can interact with the computer. So we are all already cyborgs in a way, in that your phone and your computer are extensions of yourself. And I'm sure you found, like, if you leave your phone behind, you end up tapping your pockets, and it's like having missing limb syndrome. Like, where the phone is, leaving your phone behind is kind of like a missing limb at this point. You're so used to interfacing with it. You're so used to being a de facto cyborg. So what's the limitation on a phone or a laptop? The limitation is the rate at which you can receive and send information, especially the speed with which you can send information. So if you're interacting with a phone, it's limited by the speed at which you can move your thumbs, or the speed at which you can talk into your phone. This is an extremely low data rate. Maybe it's like 10, optimistically 100 bits per second, but a computer can communicate at gigabits, terabits per second. So this is the fundamental limitation that I think we need to address to mitigate the long-term risk of artificial intelligence, and also just go along for the ride. And So, but like I said, that's an esoteric explanation that I think will appeal to a niche audience, some of whom may be here. And that's a very difficult problem. So even if we do not succeed with that problem, I think we are confident at this point that we will succeed at solving many brain injury issues, spine injury issues along the way. So so anyways. So actually we have Justin Roiland in the audience. Hi, Justin.
So it's a little Rick and Morty reference here. This great Rick and Morty episode about intelligence enhancement of your dog, and what's the worst that could happen? So anyway, Rick and Morty, I recommend it. So you want to be able to read the signals from the brain. You want to be able to write the signals. You want to be able to ultimately do that for the entire brain, and then also extend that to communicating to the rest of your nervous system if you have a sort of a severed spinal cord or neck. So now this video is now 18 months old. So this is Pager, who is playing monkey mind pong. So this is Pager has a Neuralink implant in this video, and the thing that's interesting is that you can't even see the neural implant. So we've miniaturized the neural implant to the point where it matches the thickness of the skull that is removed. So it's essentially it's sort of like having an Apple Watch or a Fitbit, replacing a piece of skull with like a smartwatch, for lack of a better analogy. So you can see, he looks he's normal. And I think that's pretty important. If you have a Neuralink device, like I could have a Neuralink device implanted right now, and you wouldn't, you wouldn't even know. I mean, hypothetically, maybe one of these demos, in fact, one of these demos I will. Yeah. So anyway, so here's first of all, it's kind of wild. Hey, monkeys can play Pong. They can actually play Pong if you give them a joystick. So Pedro first learned to play Pong with a joystick. So I'm like, that was novel. It's like I didn't know monkeys could play Pong, but they can. And then so we first trained Pedro to play Pong with a joystick. Then we took the joystick away and have the Neuralink. And now he's playing telepathic video games, essentially. So what we've been doing since then is we've been on the very difficult journey from prototype to product. And I've often said that prototypes are easy, production is hard. It's really, I'd say, 100 to 1,000 times harder to go from a prototype to a device that is safe, reliable, works under a wide range of circumstances, is affordable, and done at scale. It's insanely difficult. I mean, there's an old saying that that it's 1% inspiration, 99% perspiration, but I think it might be 99%, or 99.9% perspiration. The best example I could give of an idea being easy, but the execution being hard, is going to the moon. It's the idea of going to the moon, easy. Going to the moon, very hard. So, we've been working hard to be ready for our first human. And obviously, we want to be extremely careful and certain that it will work well before putting a device in a human. But we've submitted, I think, most of our paperwork to the FDA, and we think probably in about 6 months we should be able to have our first Neuralink in a human. So. But as I said, we do everything we possibly can to test the devices before, not even going into a human, before even going into an animal. So we do benchtop testing, we do accelerated life testing. We have a fake brain simulator that has the texture and it's like emulating a brain, but it's sort of rubber. And so before we would even think of putting a device in an animal, we do everything we possibly can with rigorous benchtop testing. So we're not cavalier in putting devices into animals. We're extremely careful, and we always want the device, whenever we do the implant, if it's in a sheep or a pig or monkey, to be confirmatory, not exploratory, so that we've done everything we possibly can with benchtop testing, and only then would we consider putting a device in an animal. Yeah, we'll actually show you a demo later today in a few hours, really, of implanting in a brain proxy. And if anyone in the audience wants to volunteer, we have the robot right there. So let's see, and since the Pager demo, we've expanded to work with a troop of 6 monkeys. We've actually upgraded Pager. They do varied tasks, and we do everything possible to ensure that things are stable and replicable, and that that the device lasts for a long time without degradation. So, and what you're seeing there is, it looks like the Matrix, but that's actually that's a real output of neural signals. So that's not a simulation or just a screensaver or something. Those are actual neurons firing. That is what one of the readouts looks like. And here you can see Sake, it's one of our other monkeys, typing on a keyboard. But now this is telepathic typing. So to be clear, he's not actually using a keyboard. He's moving the cursor with his mind to the highlighted key. Now technically, we can't actually spell, and so I don't want to oversell this thing, because that's the next version. But what's really cool here is Sake the monkey is moving the mouse cursor using just his mind, moving the cursor around to the highlighted key, and then spelling out what we want to spell. But and then so this is something that could be used for somebody who's say quadriplegic or tetraplegic human, even before we make the spinal cord stuff work, is being able to control a mouse cursor, control a phone, and we're confident that someone who has basically no other interface to the outside world would be able to control their phone better than someone who has working hands. So. Yeah. And I mentioned upgradability. Upgradability is very important because our first production device will be much like an iPhone 1. And I'm pretty sure you would not want an iPhone 1 stuck in your head if the iPhone 14 is available. So it's going to be, being able to demonstrate full reversibility and upgradability, so you can remove a device and replace it with the latest version, or if it stopped working for any reason, replace it. That's a fundamental requirement for the device at Neuralink. And I should say both Sake and Pager were upgraded to our latest and greatest implants. So that's been really over a year and a half now that Pager's had for the first implant and then the upgraded implant. So this is a very good sign that it lasts for a long time with no observed ill effects. I think it's also important to show that Sake actually likes doing the demo and is not like strapped to the chair or anything. So yeah, so the monkeys actually enjoy doing the demos because and they get the banana smoothie, and it's kind of a fun game. So. I guess the point I'm trying to make is like we care a great deal about animal welfare, and I'm pretty sure like our monkeys are pretty happy, you know. So as you can see, a quick decision maker on the fruit front. So for our, the first two applications we're going to aim for in humans are restoring vision. And I think this is like notable in that even if someone has never had vision ever, like they were born blind, we believe we can still restore vision. Because the visual part of the cortex is still there. Yeah, even if they've never seen before, we're confident that they could see. And then the other application being in the motor cortex, where we would initially enable someone who has no ability, almost no ability to operate their muscles, you know, sort of like a sort of Stephen Hawking type situation, and enable them to operate their phone faster than someone who has working hands. But then obviously even better than that would be to bridge the connection. Take the signals from the motor cortex, and let's say somebody's got a broken neck, then bridging those signals to Neuralink devices located in the spinal cord. So we're confident there are no physical limitations to enabling full body functionality. I mean, as miraculous as it may sound, we're confident that it is possible to restore full body functionality to someone who has a severed spinal cord. So, yeah. All right. And then I want to emphasize again that the primary purpose of this update is recruiting. A lot of times people think that they couldn't really work at Neuralink because they don't know anything about biology or how brains work. And the thing that we really want to emphasize here is that you don't need to, because when you break down the skills that are needed to make Neuralink work, it's actually many of the same skills that are required to make a smartwatch or modern phone work. So it's sort of, you know, software, batteries, radios, inductive charging, and you know, as well as things that are specific to us, like animal care and clinical and regulatory matters. Obviously, machine learning, that phrase is used a lot. But we obviously need to interpret the signals from the brain, which is a biological neural net, and the best thing to interpret a biological neural net is a digital neural net. So this is, if there's one message I want to convey, it is that if you have expertise in creating advanced devices like watches and phones, computers, then your capabilities would be of great use in solving these important problems. That's more than anything the message I want to convey. Let's see. Yeah. So with that, I guess, DJ. DJ's was on the founding team of Neuralink and has made immense contributions to the company, as have many of the others who will present. But I want just to thank DJ for his immense contribution to Neuralink and All right, cool, thank you.
Thanks, Elon. When I moved from South Korea at age 13 and needed to learn a new language to communicate, I wondered whether there are better and more effective means of communicating my thoughts to the outside world. And watching Neo learn Kung Fu in The Matrix, I remember thinking, wow, I want to work on that, work on making that possible. And today, I believe that this is a tractable engineering challenge. Since everything about your intentions, your thoughts, and your experiences are all in your brain, encoded as firing statistics of action potentials, if you're able to put electrodes in the right places with the right sensing and stimulation capabilities, this and many other applications that Elon talked about are possible, and we can help a lot of people. I'm incredibly excited to be working on this ambitious yet important mission to make that future a reality here at Neuralink. And I'm also incredibly honored to be working with some of the brilliant colleagues, scientists and engineers across many engineering disciplines, to work on this intersection of biology and technology. You'll hear from several of them today to learn about the breadth of technical challenges we face and our progress in the last year. And I think you'll find that for most of these challenges, as Elon mentioned, you don't need a prior understanding of how the brain works, and that a lot of what we do is applying engineering first principles to biology. So how do you create a high bandwidth generalized interface to the brain? From day one, we focused on a set of foundational technologies that are safe, scalable, and capable of accessing all areas of the brain. These three axes, safety, scalability, and access to brain regions, really form the basis for how we engineer products here at Neuralink. Safety, because we want to make our devices as well as the installation as safe as possible so that we can drive the adoption of this technology. And scalability, because as we make our devices safer and more useful, more people will want it. And with scale, we also want to make it more affordable. And access to brain regions so that we can expand the functionalities of our technologies. So our first steps along these dimensions for our device is what we call the N1 implant. It's a size of about a quarter, and it has over 1,000 channels that are capable of recording and stimulating. It's microfabricated on a flexible thin film arrays that we call threads. It's fully implantable and wireless, so no wires, and after the surgery, the implant is under the skin and it is invisible. It also has a battery that you can charge wirelessly, and you can use it at home. So similarly, for implanting our device safely into the brain, we built a surgical robot that we call the R1 robot. It's capable of maneuvering these tiny threads that are only on the order of a few red blood cells wide, and inserting them reliably into a moving brain while avoiding vasculature. It's quite good at doing this reliably. And in fact, because we've never shown an end-to-end insertion of a robot in action, we're going to do a live demo of the robot doing surgery in our brain proxy. So who wants to see some insertions? So here it is. That's our R1 robot with our patient Alpha, who is lying comfortably on the patient bed. This is what we call the targeting view. So what you're seeing is this is a picture of our brain proxy. And the pink represents the cortical surface that we want to insert our electrodes into. And the black represents the vasculatures that we want to avoid. And what you're seeing is these hash marked with numbers that represents where we intend to put each of our threads. So should we see some insertions? So this is another view real quick. On the left is the view of the insertion area. And on the right, what the robot's going to do is it's going to peel the array, the threads, one by one from its silicon backing and insert it into the targets that we predetermined in the targeting view. So there you go. That's the first insertion. So we're going to see a couple more insertions. The whole process of inserting about 64 threads in our first product is going to be around 15 minutes for this robot. So yeah, there's a second one that went in, and we're going to do a third one. There you go. And then that's going to go in the background, and we'll come back to it in the later part of the presentation. And as Elon mentioned, we've been working very hard to go from prototype to building product. As part of this, one of the things that we did is to move our device manufacturing to a dedicated facility in Austin for scale-up manufacturing. And what's important to highlight, and is evident in this clip, is that it's very typical for us to have our engineers who design also work on the physical manufacturing line to build and debug. And this has been extremely, extremely critical in reducing our iteration cycle time. And we've also scaled up our surgery. So we now have a dedicated, our own OR, in fact, a double OR in Austin. And this is just a stepping stone before we eventually build our own Neuralink clinic. So with this product, N1 and R1, our initial goal is to help people with paralysis from complete spinal cord injury regain their digital freedom by enabling them to use their devices as good as, if not better, than they could before the injury. And as Elon mentioned, over the last year, this has been the central focus of the company. And we've been working very closely with the FDA to get approval and to launch our first in-human clinical trial in the US, hopefully in the next 6 months. So hopefully this gives you a good overview of our product. For the next hour, we're going to go through a deep technical dives on these topics to tell you about our technical challenges, share some of our progress, and preview what's coming next. So with that, over to Nir from my team, who's going to talk to you about neural decoding.
Thank you, DJ. And hey, everyone. My name is Nir Evan-Chen, and I'm the head of Brain Interfaces Applications. Our goal is to enable someone with paralysis control a computer, as well as me, or even better. We'd like to provide fast and accurate control with all the functionality of computers that works anytime, anywhere. So I'm very excited to show you how we're using the N1 device with our software and algorithms to achieve this. Last year, we shared with you a video of Pedro the monkey controlling a computer cursor with his brain. So how do we do that? Just a brief reminder. First, we record his neural activity from the motor cortex using the N1 device. We can record from over thousands of channels while he's playing with the joystick. Then we can train a neural net that predicts the cursor velocity from the patterns of his neural activity. With this decoder, he can then control a cursor just by thinking about it, without even moving the joystick. He can play with this decoder a variety of games, also a grid task, where he's moving the white dot towards the yellow target. Every time he gets one, he receives a drop of his favorite smoothie. And he chooses to play this game every day. Here you can see his performance from early 2021, around the time we released the previous demo. It's quite accurate, but it's a bit slower than what we would like. And cursor control is the foundation for interacting with most computer applications. So since then, we've been working to improve cursor speed and accuracy. As you can see, it's much, much faster, almost twice as fast. However, it's still a bit slower than what I can do. So we are working on creative ways to improve that. Now, speed is not enough. You want a full set of functionalities. And for decades, most software was built for mouse and keyboard control. And it doesn't make sense to reinvent this entire ecosystem for brain control, at least for now. So we are working and we are designing mouse and keyboard interfaces for the brain. The way we do that is by training Pager and his friends on a variety of computer tasks, and then designing algorithms to predict their behavior. Here you can see a few examples of tasks in different phases of monkey training. For example, left and right click, click and drag, cursor typing, swipe typing, handwriting, and even hand gestures. Now, interacting with computer is bidirectional, and feedback is very important. I like when I click on a button and I can physically feel the button being pressed. When a potential N1 user will attempt to click, they won't be able to feel it. An example of how we are addressing that is by providing a real-time visual feedback that represents the strength of the neural click by changing the color of the cursor. Just by typing on a physical keyboard is much faster and easier than typing on an iPad keyboard. This will make the brain control much faster and easier to use. Typing, one of the most important functionalities. So you already seen this message, and I want to show you the behind the scene of how this message was created. And here you can see again Saki using the virtual keyboard, typing this message. This virtual keyboard is similar to the one I use on my phone. And with the speed and accuracy that we achieved so far, typing on a virtual keyboard is already fast and easy. However, I never use a virtual keyboard when I type on my computer, because it covers my screen, and it's also much slower than what I can do with my 10 fingers. We can do better. For example, a group from Stanford asked a person to imagine handwriting letters. Then they decoded the letters from his brain activity. Using this approach, they were able to speed up the typing rate. We started this project with our monkeys, but of course they don't know how to write. So to mimic writing, we trained Ranger, one of our favorite monkeys, to trace digits on an iPad. Here you can see him tracing the digit 5 and the digit 2. Then we recorded his neural activity with the N1 device. But now, instead of decoding the cursor velocity, we decode in real time the digit that he's tracing on the screen. We had two main takeaways from this project. One, that monkeys are awesome and can learn very, very complex tasks. The second one, that although it can increase the typing rate, it requires hundreds of examples and samples of each of the digits and the characters we wanted to classify. This would not scale. The way we are solving that is by indirection. Instead of decoding directly the digits, we first decode the hand trajectory on the screen. And then, when we decoded the hand trajectory, we can use any off-the-shelf handwriting classifier to predict the digit and the characters. For example, classifiers that are trained on an MNIST dataset. Why it's so important? It's important because now we can potentially decode any character in any language with only one neural decoder for hand trajectory. It means that you can write in English, Hebrew, Mandarin, or even monkey language, and we can understand you wanted a banana. So there are many challenges ahead of us to improve functionality and speed. And I want to hand it off to Bliss to talk about the third part, how we are making our brain interfaces work anytime, anywhere.
Hello, everyone. My name is Bliss, and I'm a software engineer here at Neuralink. When I use my computer, my mouse and keyboard work how I intend them to. at least like 99.9999% of the time. My goal is to enable a user with paralysis to control their computer as reliably as I can. Here's what we want that experience to feel like. In this video, you can see Saki walking over to his MacBook and choosing to work on his typing task. The entire decoding system works out of the box, and it feels totally plug and play. The first step to achieving this kind of high reliability is to test extensively offline. A typical flow for using the N1 link is to connect over Bluetooth, stream out neural activity from the brain, and then use that neural activity to train decoders and do real-time inference. We've built a simulation for exactly this sequence, but instead of using a monkey with an implant, we use a simulated brain that injects synthetic neural activity into an implant sitting in a server rack. From the point of view of that implant, it's in a real brain. This simulation runs on every code commit to validate that from the hardware all the way up through to the neural decoders, our entire stack can achieve state-of-the-art performance. However, while this kind of simulation is great for integration testing of software and hardware, it's not yet detailed enough to guarantee high reliability in the real world. In the real world, the underlying signals we're trying to decode actually change day to day. In this plot, you can see the average firing rate detected on a representative channel of Saki's implant. Each bar represents one day, and you can see that each day has a different average firing rate than the previous. This presents us with a very interesting problem for how to make our decoders robust day to day. It can actually happen that if you train a neural decoder on one day of data and then try to use it on the next, the average firing rates can actually shift enough to cause a bias in the output of the model. Here on the right, you can see that this bias is making it hard for the cursor to move to the upper right corner. You see it struggling here to make it up to the upper right, and then it moves much more effortlessly down to the bottom left. We're trying many approaches to mitigate this problem. Some examples include building models on large data sets of many days of data to try to find patterns of neural activity that are stable across days. Another approach we're trying is to continuously sample statistics of neural activity on the implant and use the latest estimates to pre-process the data before feeding it into the model. This is really an active area of research for the team, and it's a critical problem to solve if we want to enable someone with paralysis to control their computer as well as I can. Another big problem we have is to minimize the time it takes for a spike in the brain to impact the movement of the cursor on the screen. If you have lag or jitter in this control loop, the cursor becomes hard to control, leading to the kinds of overshoots that you can see here on the right. One big improvement we've made towards in this direction is called phase lock. Phase lock aligns the edge of each packet that we send off the implant to the exact moment that the Bluetooth radio is going to wake up. This minimizes the time it takes for a spike in the brain to be incorporated into the prediction of our neural network. Here you can see the latency distribution after phase lock. Not only has the mean been greatly reduced, but the variance has been reduced as well. This makes it easier for the user to predict the behavior of their cursor. Over the last year, we've made tremendous improvements to the stability and reliability of our system. And we've been able to demonstrate consistent high performance across many sessions and many months. However, there's still a long road ahead of us before the system will truly feel plug and play. So if solving the hard problems required to ship this technology is exciting to you, you should consider applying to join the team. Now, I'm going to hand it over to Avinash to talk about how our custom low-power ASIC detects spikes in the brain.
Hi, I'm Avinash, one of the engineers on the ASIC team. We designed the custom neural sensors, which include both analog and digital circuitry, to record and stimulate across 1,024 independent channels. We face challenges across all three major metrics: performance, power, and area. Not only do we have to fit all 1024 channels into a single quarter-sized implant, but we also have to measure spiking activity less than 20 microvolts in amplitude. And today, I'd like to focus on the last challenge I mentioned, power. Power consumption is important to us because we want to give future users a full day of use of their implant without any interruption for charging. Back in 2018, we were sending every sample from every channel off the device for processing, which burned a ton of power. In 2020, we brought spike detection onto the chip. As you may know, neurons transmit information by firing. So simply monitoring for these spikes and only sending these spike events off the implant acts as a very efficient form of compression. And over the past 2 years, we've continued to make optimizations within the ASIC, dropping the total system power consumption down to just 32 milliwatts and doubling battery life. Let's take a look at our on-chip spike detection algorithm, which makes our battery-powered implants possible. We first start by applying a 500 Hz to 5 kHz bandpass filter to remove noise that's out of band. Next, we use an estimate of the noise floor to generate an adaptive threshold per channel. And finally, our spike detector module identifies 3 key points of a spike. Identifying 3 points allows us to detect not just the presence of a spike, but the shape of a spike as well. This can be extremely important for distinguishing between multiple neurons adjacent to a single channel. Today, I'd like to focus on one of the many optimizations that we've made in our latest chip. This one specifically cutting system power by 15%. Note that neurons spike relatively infrequently, which means that our spike detector spends a lot of time searching for the first point of a spike and very little time searching for the other 2 points of a spike that only occur after the threshold is crossed. We can use this characteristic of the input waveform to reduce memory accesses within the chip by 30%. Let's take a look at how that works. Our spike detector is implemented as a single functional unit that's shared across all channels with an SRAM to buffer the state of each channel. As a sample comes in, its channel state is read from SRAM, an incremental spike detection step is run, and then the updated state is written back to SRAM. Since this is happening 20 million times per second across the implant, each of these accesses add up quite quickly. In our latest chip, we split the state into 2 parts, a hot state and a cold state. The hot state is accessed on every cycle, while the cold state is only accessed once the threshold is crossed, reducing the average access width and saving power. We're also working on a next generation stimulation-focused chip with 4,096 channels still within the footprint of our current chips. In addition to increasing the channel count, we're also increasing the drive voltage so we can get better activation per channel. And to support this higher channel count, as well as a broad range of future applications that you'll soon hear about, we're adding an ARM core onto the chip. And finally, since these chips are the same size as our current chips, we can still put 4 of them together into a single implant for a total of 16,000 channels still within the size of a quarter. As you can see, we've been working very hard to improve the power consumption within the implant. But we've also been working very hard to improve the charging experience of the implant, which Matt will talk about. But first, the robot has just completed inserting all 64 threads. So let's take a look. This is a view of the insertion site, similar to the one that DJ showed you earlier. But instead of the targeting reticles, if you look closely, you can see that all 64 threads, each carrying 16 electrodes, have been inserted into the brain proxy while avoiding vasculature, and all just within the past 20 minutes. Let's hand it over to Matt now to continue the technical deep dive.
Hi, I'm Matt, head of Brain Interfaces Electrical Engineering. Our fully implantable N1 device depends on a battery for continuous operation. When that battery is running low, charging is accomplished through wireless power transfer. However, unlike many consumer electronic devices, which can simply offer a physical connector, charging a fully implantable device poses several unique challenges. First, the system must operate over a wide charging volume without relying on magnets for perfect alignment. The system must be robust to disturbance and complete quickly so as not to be overly burdensome. However, most important is safety. In contact with brain tissue, the outer surface of the implant must not rise more than 2 degrees C. In pursuit of these goals, our charging system has gone through several engineering iterations. The first, if you watched our pig demo in August of 2020, Gertrude was implanted with a version of the N1 charged with our first generation charger. This device was implemented in a small puck package and later separated into a remote coil and battery base. This charger was challenging to use. However, we learned a lot through its implementation. Our current production charger, which charges our current generation of implants, is implemented in an aluminum battery base, which also includes the drive circuitry. A remote coil, 4 times the size of our original device, also disconnectable. This remote coil has increased switching frequency, driving improved coil coupling. This charger is in use today, including several applications within our engineering and animal test facilities. I'd like to show you one of these applications here with a device we call our simple charger. And the coil has been embedded into the habitat. With the addition of one new outer control loop plus a banana smoothie pump, the troop has been trained to charge themselves. So let's see how Pager charges his implant. On the right, we're streaming real-time diagnostics from Pager's N1. When he climbs up and sits below the coil, you can see the charger automatically detect his presence and transition from searching to charging. We see the regulated power output on a scale of 0 to 1 and the current driven into his battery. I mentioned earlier that we improved the coil coupling. However, the high quality factor coils exhibit good charging performance over relatively larger distances, but as they're brought closer to the implant, what you see is a peak splitting effect, where the best, highest efficiency power transfer is pushed up into higher frequencies outside of the ISM band, required for compliance with regulated radiated emissions. In our next generation charger, we address this problem by the introduction of dynamic tuning, shown on the right. This allows us to, in real time, adjust the resonant frequency of the transmit and receive coils so that we can change their properties just ahead of degraded performance. The electrical engineering team is currently engaged in developing a 3rd generation charger. Notable improvements include bidirectional near-field communication. This has allowed us to reduce the control latency and improve the thermal regulation. Improved thermal regulation results in faster charge times. And now, Julian will tell us about how we test the N1.
Thank you very much, Matt. My name is Julian, and I lead the embedded software group on the Brain Interfaces team. So when we started building implants, we had a small manufacturing line, and to collect data from an implant, you would manually walk over with your laptop, you would connect, and collect the data of interest. But our goal is to make an ultra-safe and ultra-reliable implant. And so to do this, we scaled up the manufacturing line, our testing throughput, and data collection capabilities. So firstly, we added a large suite of acceptance tests to the manufacturing line. These test the functionality of each component and the final assembly. Implants coming off the line are then subjected to benchtop testing, accelerated lifetime, and animal models. We then collect data from these implants round the clock. This data is processed by a series of cloud workers and displayed in an aggregate manner. And then finally, all of this information feeds back into our design process and empowers our engineers to answer any question about any implant at any time. I'm now going to walk you through different parts of this infrastructure, starting off with firmware testing. So the implant contains a small microprocessor running firmware to manage a whole bunch of its operations. And before we release a firmware update, we want to rigorously test it with both unit and hardware-in-the-loop tests, also known as hill tests. So to do a hill test, what you do is you instrument the battery, you instrument the power rails, the microprocessor, and then we connect to each device with a Bluetooth client, and then we walk the devices through various scenarios to test things like power consumption, real-time performance, security systems, fault recovery mechanisms, a lot of different things. In our original implementation of these systems, we used off-the-shelf components to start automating tests quickly. However, these systems were constructed in a relatively artisan fashion and were very difficult to maintain. And this meant that testing quickly became the bottleneck for development. So to alleviate this, the hardware and software teams developed a new system which integrates all the required components onto a single baseboard. We can then put the charger and implant hardware on individual modules that plug into this baseboard, including one board with opposing coils so that we can test charging performance. This architecture allows us to rapidly iterate different hardware prototypes because we can simply drop them into this system and reuse all the testing infrastructure. Additionally, we can host the current and next generation of our neural ASICs onto FPGAs and plug those into this board as well. And that allows us to test a whole extra layer altogether. So that's how we generated this rather inceptive image here on the right. What you're looking at is spiking activity emitted from some of our simulated neural sensors, streamed through the entire system over Bluetooth, and then displayed on a phone. This allows us to test everything in one system, from chip to cloud. This system is 1/5 the cost, 1/5 the volume, and is very easy to manufacture. This allows every developer to have a personal unit on their desk, and it also allows us to shard the entire test suite over a large number of these units mounted into a rack. All of this has greatly accelerated our rate of development. Let's look next at how we monitor the implant's electronics, the battery, and the enclosure. So the implant will periodically capture all of its vital signs and commit those to flash. And then upon next connection with one of our recording stations, it will stream that data off. So for instance, if we look at humidity, we can get an understanding of the integrity of the implant's enclosure. And by looking at battery voltage and power measurements, we can gauge battery health. All of this is done automatically without any intervention, giving us 24/7 visibility into the quality of every single device. Additionally, we can use this infrastructure to request high fidelity information on demand so that we can investigate different anomalous situations. So for instance, in this particular scenario, we were trying to track down the source of some spurious spikes that we were observing on different channels, and so we requested raw wave samples directly from those channels. Capturing good quality neural signals requires intact, low impedance electrodes. And so this is also something we monitor very closely with dedicated circuitry on the neural sensor. So how do we do this? We do this by first using an onboard DAC to play a test tone on a single channel. And then we record, using our ADCs simultaneously, we record the response signal on both that channel and physically adjacent channels. Not only can we measure the impedance of every channel with this, but we can also map different physical phenomena to different characteristic signatures. So for instance, an open channel will appear as a very large response on the channel, and shorter channels will appear as a large response on neighboring channels. By looking at the purity of the signal coming back, we can also validate that the analog front end of the neural sensor itself is operational. In our original implementation of doing these impedance scans, it took 4 hours to get through all 1,000 channels. But by parallelizing the tests, downsampling, filtering, and then reducing the amount of information we have to stream off the device by moving a lot of the calculation to the firmware side, we're now able to scan all 1,000 channels in just 20 seconds. This means that we can run impedance on every implant every day. And then our internal dashboards can play back a history of this impedance so that we can get a really good quantitative insight into that interface between biology and electronics. Now that you have an idea about how we test and monitor our implants, I'm going to hand it off to Josh, who's going to tell you about how we get feedback even faster by accelerating our implants to failure.
Hello, my name is Joshua Hess, and I'm an engineer on the Brain Interfaces team. We are responsible for the implant system design, as well as many of the manufacturing and testing tools. Julian just talked to you a little bit about some of the ways in which we test our implant electronics hardware and software. But what about the entire system as it relates to longevity in tissue? One of the ways we've addressed this is with the development of our in-house accelerated lifetime testing system. The system allows us to expedite and capture long-duration implant failure modes at scale to rapidly increase our pace of iteration. Even better, the system also significantly reduces the amount of tests which require animal models, both for implant prototypes and, of course, longevity testing. So how does the system work? Well, at a very basic level, it comes down to three things. First, we want to mimic the internal chemistry of tissue. Next, we want to accelerate these chemical interactions as well as diffusion with our implant materials. And finally, we want to aggressively cycle the internal electronics of our implant. With these things, primarily the first two, we have achieved a conservative 4x acceleration factor by the Arrhenius relationship. In other words, every day our implants spend in our accelerated system is equivalent to at least 4 days spent in vivo. Historically, one of our greatest challenges has been the battle against moisture ingress into our implants. So we continuously monitor the internal humidity to watch for abnormal rise. Here, in white, you can see some internal humidity data from implants in some of our animals for the duration of over 1 year. As you can see, our internal humidity sensing is so sensitive, it can even detect the very small and slow humidity rise just from diffusion through our implant materials. Now, in blue, you can see that same internal humidity data, but from devices in our accelerated system. Now, if we adjust this data for our acceleration factor, you can begin to see not only the agreement in this data, but also just how far into the future this data extends. Now, in red, you can see a device which has failed in our accelerated system. This device showed an abnormal increase in humidity over the duration of many months before implant electronic failures occurred. So how do we build this system? Well, we started building the first system prototype just after the COVID shutdown had begun in early 2020. So we had to get a little creative. As you can see, our first system prototype was a little scrappy and operated out of one of our apartments, as indicated by the carpeting. Although scrappy, the system allowed us the fastest path to start testing our devices, tuning our working fluid chemistry, and checking our constraints. We also immediately started root causing observed failures in early implant prototypes, fed that information into the next prototype designs, and literally rinsed and repeated. Over the duration of just a few months, the system was built out totally custom and highly iterated with 2 system versions and countless minor iterations, leading us to our currently operated 3rd generation system, which achieves high density testing with automatic in-vessel charging as well as automatic data collection. The system also features an implant sled assembly, which accepts brain proxy material such that the implant can be installed and inserted by the surgical robot, just like you saw a few minutes ago. We also integrated the system into a high-density rack mount form factor, along with a centralized fluid management system, both for chemical uniformity across vessels and also reduced operational maintenance. The system has been in operation for the last 1.5 years and has had its fair share of challenges. Since the system itself is undergoing the same accelerated abuse as the implants within it, it has been extremely challenging to design, build, and maintain a system of this scale while keeping it robust, even against itself. So what comes next? Well, we have started work on our 4th generation system and have totally redesigned it from the ground up to be a hot swappable, single implant per vessel design, partly inspired by high density compute servers. With this new system, we will achieve a whole new level of density, robustness, and scale. We also intend to have many of these systems operational in the pursuit of capturing even the lowest frequency edge case failure modes. With this, we will have thousands of implants testing in pursuit of these goals. We've already started work building out this system, but there is still a lot left to do. There are also many exciting challenges ahead of us, such as introducing mechanical stressing, brain proxy micromotion, and even replicating tissue growth around the threads for more complete and representative accelerated testing. So now that you've heard some of the ways in which we rigorously test our implant designs before production for surgery, Christine is now going to take you through a detailed look at our surgical process.
Thanks, Josh. Hi, everyone. I'm Christine, lead of the surgery engineering team. To get an N1 device, it's essentially these steps: targeting and the incision, drill the craniectomy, remove the tough outer meningeal layer called the dura, then insert the thin, flexible threads of electrodes, place the implant into the hole we created, and then that's it. You've got an implant under the skin. Look, Ma, no wires. Just kidding. I mean, seriously, no wires, but I don't actually have one. The surgical robot does the thread insertion part of the surgery. This is because it would be very difficult to do manually. Imagine taking a hair from your head and trying to stick it into Jell-O covered by saran wrap, and doing this at a precise depth and position, and doing this 64 times within a reasonable amount of time. And a neurosurgeon would probably not like it very much if we asked them to do this for the surgery. So we have the robot that you saw doing its tiny dance. I sort of wanted to call it Tiny Dancer, but it's called R1, which is also great. The rest of the surgery is done by the neurosurgeon. In order for us to make an accessible and affordable procedure, we need to revisit this. I'll tell you why. When I was in school, my dad lost the ability to walk and to use his arms and even to speak. He was diagnosed with ALS. We would look on the internet and you could see maybe one person here or there who had some cool custom robotic assistive device, but it was deeply frustrating how limited were the options available to him. And there's hundreds of thousands of people with paresis, not even counting people with other conditions that our device might be able to help. Meanwhile, there's not that many neurosurgeons, maybe about 10 per million people. And it takes about a decade or more to train a neurosurgeon, and they're already generally very busy. And as you can imagine, their time is very expensive. So in order for us to do the most good and have an affordable and accessible procedure, we need to figure out how one neurosurgeon could oversee many procedures at the same time. This might sound sort of crazy, but probably so did laser eye surgery before LASIK made it normal. LASIK's been around for about 30 years and counting. In the beginning, the laser robot did just the most fundamental core part that it had to do, and the surgeon did the rest. And over the iterations, the surgeon has to do less and less, and the laser robot does most of it. And it's a highly compelling procedure, takes just a handful of minutes, and often gives life-changing results. Since I joined in 2017, we've also done a handful of iterations to optimize the thread insertions of the robot. One of the challenges that we've had to face has to do with the optomechanical packaging. So as you can see here, there's about 3 primary optical paths that are really valuable for us to have reliable thread insertions. One is the visible imaging of the needle inserting the thread. And then another is the laser interferometry system called OCT, optical coherence tomography, that gives us the precise position of the brain while it's moving in real time. And then also we have to provide lighting and illumination to see what's going on in the visible light camera. And doing all this where the needle is at the bottom of the craniectomy, especially when it's close to the skull wall, can be pretty difficult to fit everything and be able to see it. So the way that the team solved this is by putting all 3 of these optical paths into one optical stack using photon magic or polarization, whatever you want to call it. And that enables us to do vessel avoidance in real time. So as I mentioned, the brain is moving, and where we place targets in the beginning may not be where you want to insert at the moment the needle is going down there. So the robot can actually detect the vessels and then determine if we're going to insert onto a vessel or not, if it's safe to insert, and then that way we can avoid inserting onto major vessels. And that brings us to the robot that we have here today. There's still a lot for us to do to get to that procedure where we reduce the role of the neurosurgeon and make it affordable and accessible. The 2 elements of the surgery that demand the most skills from the neurosurgeon are the craniectomy and the directomy. Alex and Sam are going to tell you a bit more about how we think we can get rid of the directomy step. So that leaves the craniectomy. In neurosurgery, if your craniectomy is small enough, you can use a standard tool called a perforator, which makes quick work of this job. But for a larger craniectomy, the surgeon has to rely on their skill in order to accommodate the variability patient to patient in skull thickness, skull hardness. Even within the same patient, in the same craniectomy, you can have different skull thicknesses, for example. In addition, if we can make something that has a very high precision craniectomy, we can open the design space for future ways of mounting the implant to the skull. So I'll show you a few of our prototypes. Ultrasonic cutters, like what's on the screen, and oscillating cutters have the benefit of not cutting soft tissue. You can cut the bone and not the brain. But however, as you can see here, our ultrasonic cutter prototype created quite a bit of heat to cut at the rate that we wanted. So onto the oscillating saw. Here, we designed a blade to minimize cut time and also conducted sound and also heating. And as you can see, you can cut through hard things like bone, but not soft things like skin. It's simple and it works. However, if you wanted to cut an arbitrary depth or arbitrary shape, the oscillating saw just won't cut it. I was afraid no one would get it. You guys are smart. There's a time-tested solution for drilling arbitrary shapes, which is a CNC drill. The challenge with us doing this on a person is that we need to make sure it cuts reliably every single time, doesn't cut too deep. And a few ways that we're using feedback to make sure we don't cut through the brain are force feedback and also impedance. And if I could get a volunteer, no, just kidding. Maybe next time. But yeah, so this is some insight into some of the things we're working on to make an accessible and affordable procedure. And now Alex is going to tell you a bit about our next generation developments.
Thanks, Christine. I'm Alex. I'm a mechanical engineer here on the robotics team. Now that we've covered the technology and surgical process for our current device, we'd like to cover some of our next generation development projects. I and the next couple speakers would like to talk about one of those projects, which is enabling device upgradability. You've gotten to hear about the advancements we've made over the past year. We've improved implant robustness, battery and charging performance, Bluetooth usability. Realistically, every new device version is going to be significantly better. It'll be more functional, it'll last longer. We need to keep this new technology accessible for our early adopters. This means that we need a solution to make device upgrade or replacement just as easy as it is to initially install. As many medical device companies have found, this is a challenging problem. The body's healing response doesn't make this easy, so this isn't solved yet. But we've made significant progress towards enabling this that we'd like to cover today. Now, we'll have to start with some background as to what makes device upgrade challenging. And we'll start with the anatomy. Under the skin, you have the skull. Below that, the dura, a tough membrane that separates the bone from the brain. And between the dura and the brain, you have the pia-arachnoid complex, a fluid-filled suspension for the brain. To install the device, the surgeon removes a disc of skull and dura to expose the brain surface. The device then replaces the removed material. The challenge is here at this interface. Over months, all empty volume is filled by tissue, encapsulating the device and the threads. The device would be trivially easy to remove. Because of the thread's small size, they would slip right out of the brain. It's the tissue layer that forms above the surface that makes the removal challenging. We've built tools in-house to study this response and characterize it, such as histology and micro-CT. In these images, you can see that layer of tissue that has formed above the surface, encapsulating the threads and adhering to the surrounding tissue. We've explored many different avenues for designing around this healing process and finding a solution to make device upgrade seamless. Our best successes have come from making the procedure less invasive. Instead of directly exposing the brain's surface, we instead keep the dura in place, maintaining the body's natural protective barrier. This prevents encapsulation at the brain's surface. And really, this is actually a huge win for making the surgery simpler and safer, as Christine alluded to. However, This doesn't come for free. The Dura is a very tough, opaque membrane. As you can see in these SEM images, it's composed of a dense network of collagen fibers. These offer an array of technical challenges for inserting our electrodes. One of those challenges is imaging through the Dura. As you can see on the left, our current custom optical systems offer pretty incredible capabilities for imaging the exposed brain surface. However, as you can see on the right, once the Dura is in place, you can't see the dense vasculature at the brain surface. The Dura is in the way. There's simply too much attenuation. To solve this problem, we're developing a new optical system that uses medical standard fluorescent dye to image vessels underneath the tissue. Here, you can see that dye perfusing through the vessels, highlighting them. There's still a lot of engineering work to go to prove accuracy and repeatability of this system, but once that's done, this will allow us to target and avoid blood vessels underneath the Dura. We're also exploring applying our laser imaging system to deeper tissue structures. In the bottom left, you can see a section of the tissue layers underneath the Dura. This image is compiled from multiple volumes from our optical coherence tomography system. You can see the collage of those volumes above. In the future, these new systems, when combined with correlation to pre-op imaging, such as MRI, will enable precise targeting without directly exposing the brain surface. Now, imaging isn't the only challenge that comes with the tough dural anatomy. Now, I'd like to hand it over to Sam to talk about some of the challenges of inserting our electrodes through this membrane.
Thanks, Alex. Hey, I'm Sam, and I lead the needle manufacturing and design team. So, as Alex mentioned, the same properties of the Dura that make it a good protector of the brain also make it really difficult for us to insert the threads into. In humans, the Dura can be over 1 millimeter in thickness, which doesn't sound like a lot, but compared to our 40-micron needles, it actually is a lot. For example, if you scaled up the needles to the size of a pencil, the Dura would scale to over 4 inches in thickness. Take a look at how far you have to zoom in to even see it. By the time the features of the needle come into frame, you could see individual red blood cells in the same frame. This is just wait. This is a real-life SEM image of our latest design. On the left there, you can see the end of the thread. In the middle is the needle, and on the right is actually a piece of my hair. So yeah, it's extremely small. And besides being really small, there's a lot of other challenges associated with designing this. One challenge is that we have to use the needle and the protective cannula that it sits in to grab onto the thread and to hold it while we peel it from this protective silicon backing. And then we have to keep holding it while we bring it over to the surface and then release it from the cannula during insertions. Another challenge is that the brain is really soft beneath the tough Dura. And so if the needle isn't sharp enough, it'll just keep dimpling the surface without puncturing. And if this free length gets too long, it can actually just buckle the needle like this. Another challenge is that we don't just have to get the needle through, we have to get the thread through as well. So we really have to focus on optimizing the combined profile of the needle and thread together. Now, these are just some of the challenges associated with designing something like this. And so far, we found that the key to solving this problem has been improving on our speed of iteration. But let's look at how we make these things in the first place. So we start with a length of 40-micron wire made out of tungsten and alloyed with a little bit of rhenium for added ductility. We designed this femtosecond laser mill in-house to cut the features of the needle and cannula. And it can do this with sub-micron precision. We spent a lot of time this year turning this thing from a science project into an industrial system. Just a couple months ago, it took a skilled operator 22 minutes to make a needle. And even a skilled operator could only get about 58% yield. Today, that same process takes just 6 minutes, and anyone can get 91% yield with just a few minutes of training. With only one click, the mill cuts and measures the needle and cannula and uploads the measurements to our limb system so that the robots can use the exact dimensions for each needle that it uses. Now, this is all for our current design, though, and we've had a couple years to optimize the manufacturing process of it. The current design has served us well so far, but it doesn't quite protect the thread well enough to get through the tough Dura. So, like I said, we had to come up with something new, and we needed to be able to iterate on designs quickly. Unsurprisingly, there's no page in machinery's handbook for this kind of thing, so we dug into the science of femtosecond laser ablation and figured out a workflow that allows us to use our laser mill much like a CNC mill. This allows us to iterate several times. This allows us to iterate in under an hour for new designs, allowing several iterations per day when we're really on a roll. As a result, the latest design, seen on the right, can actually insert through 9 layers of Dura, totaling 3 millimeters on the benchtop. This is far more than we could ever expect in a human with significant margin. The needle isn't the only part of the puzzle, though. As you can imagine, all of these designs here work with different threads. So we need a way to iterate on that as well. And we do this by having our microfabrication process here in-house. This summer, we completely rebuilt our clean room in about 9 weeks, which, among other things, greatly reduced particulate counts, which allows yield and throughput to greatly increase. This, combined with all the other great improvements the microfab team has made, allows us to iterate on new designs in just a matter of days. The last piece of the puzzle, though, is testing. We can come up with as many new designs as we want, but unless we have a way to actually test them in the right conditions, we won't know what to tweak. Or even worse, we'll spend time optimizing for the wrong things. Take this failure mode, for example. A few months ago, we got to the point where we could pretty reliably insert through the Dura. But when we took the proxies and put them in our micro CT imaging, we realized that our hold on the end of the threads was actually too strong, and we were pulling them out just a little bit underneath the surface. By the time we solved the problem, we realized that this issue was very sensitive to the properties of the surrounding material or tissue. We could make a proxy where this never happens, and we could make another proxy where this happened every single time. And this highlights why it's crucial that we spend time making our benchtop tests match tissue as accurately as possible. And I'm going to pass it off to Leslie now, who's going to talk about how we've been doing that. Thanks.
Hi, I'm Leslie, and I lead microfabrication R&D. And part of what we're interested in is understanding the biological environment our implant and threads experience once they're fully installed in the body. Learning directly from biology, though, is inherently slow. So in order to move fast, we're developing synthetic materials that mimic the biological environment. This allows us to learn as much as we can on benchtop and start taking steps away from the industry standard of animal testing. Developing accurate proxies, though, is challenging. The implant environment is made up of many anatomical layers that all have unique properties. And as time goes on and the implant site heals, new tissue forms, filling any available space. In addition to that, motion related to cardiovascular activity and head movement introduce added complexity. So to start addressing some of these challenges, we're engineering materials using feedback from biology. This may involve mechanical characterization of tissue or analysis of interactions at thread-tissue interfaces. Much of this characterization is even done during surgery itself by using custom hardware and software that modifies our surgical robot to double up as a sensitive characterization tool. We then use the data collected and feed it back into optimizing our materials so that they behave mechanically, chemically, and as shown here, structurally, just like biology. We've come a long way from our humble first brain proxy, shown here sitting on a plate and consisting of agar and a parafilm sheet. And while simple, it allowed us to perfect robot insertions through countless benchtop tests. Today, our proxy is slightly more complex, where we've upgraded to a composite hydrogel-based brain proxy that better mimics the modulus of real human brain. We've also incorporated a Dura proxy and developed an injectable soft tissue proxy that so far has allowed us to perform benchtop mock explant testing. We have a super long wish list for our proxy of the future, but some of those items include a surgery proxy with integrated soft tissue, brain, bone, skin, or even a whole body, a brain proxy that simulates motion, vasculature, and electrophysiological activity, and a biological proxy to test biocompatibility and electrical stimulation. There's a ton of ongoing work getting us closer to our proxy of the future, including work on lab-grown cerebral organoids, as shown here. And all of this will get us closer to a future where we learn more and iterate faster on benchtop and reduce our reliance on animal models, or even one day replace them completely. And with that, I'll hand it over to Dan, who will be presenting a very exciting next generation application. Thank you.
Thank you, Leslie. My name's Dan, and I came to work at Neuralink after following a career in visual neuroscience research. I was inspired to join this company because I saw in our device the potential to restore vision to people rendered blind by eye injury or disease. There are a number of particular characteristics of our device that make it uniquely suited to this application. Firstly, as well as being able to record from every channel, we can stimulate neural activity in the brain by injecting current through every channel. This is important because it allows us to bypass the eye and generate a visual image in the brain directly. Secondly, our device can have an enormous number of electrodes. For a visual prosthesis, this is important because the more electrodes you can have, the higher density of an image you can create in the brain. Thirdly, thanks to our robot, we can insert these electrodes deeply into the brain. Now, this is an important thing for a visual prosthesis because the human visual cortex is buried deeply in a fold in the medial face of the brain called the calcarine sulcus. In this image, I've highlighted the calcarine sulcus in red in an MRI. It contains a map of the visual world, the visual field. It's about a surface area equal to a credit card on each side. And if you unfold it and flatten it, you see that the image is inverted, it's upside down. But more interestingly, it's distorted so that the central part of the visual field, the fixation point, is greatly magnified. So for example, if you look at this image of Lincoln, if you look directly into his right eye, everything to the left of that fixation point is directed to your right visual cortex, and everything to the right goes to your left visual cortex. His eye, even though it's very small in the image, is magnified in the brain to occupy nearly a quarter of the surface area of the visual cortex. Over the last half century, visual neuroscientists have developed a profound understanding of visual processing in the brain. What's driven most of this research is recording from single cells in the cortex, usually of macaque monkeys. One of the seminal discoveries was that every cell in the visual cortex represents only a tiny part of the visual field. Your perception is made up of a mosaic of tiny receptive fields, each belonging to a single cell in your visual cortex. So if you record from one of these cells in a monkey, say in this location, you can find a very tiny region of the screen where a light stimulus will cause modulation of that neuron. Another location in visual cortex will have a location elsewhere on the screen, in this case in the lower visual field. These regions are called receptive fields. We've inserted our device into the visual cortex of 2 rhesus monkeys, whose names are Code and Dash. That means we can record activity from their visual cortex generated by their normal home environment as they roam around. But as we all know, monkeys love banana smoothie. That means we can easily teach them to fixate points on a screen and reward them. We can reward them very precisely because we can track the location of their eye using an infrared camera. One of the things this allows us to do is to plot the receptive fields for every neuron that we can record with a single device. Now we do this by showing the animal a movie of random checkerboards whilst he fixates steadily on the screen. Then we take only the frames of the movie that generated a response in the cell and average them all together. This is a technique known as reverse correlation. It's generally used quite widely in visual neuroscience for this purpose. And this is an example of a receptive field plotted with this technique. The central cross is the fixation point, and you can see the little red and blue regions of excitatory and inhibitory receptive field, these regions give cortical cells some of their characteristic properties. So we can record all the receptive fields from all the electrodes at the same time. And if we take all these receptive fields and accumulate them together, overlap them, and place them on a computer monitor for scale at a typical viewing distance, you begin to get an idea of how much of the visual field we can cover with this preliminary device. Many of the receptive fields are close to the fovea, close to the fixation point. That's partly due to the magnification that I talked about of the fovea. But there's also a scattering of fields in the periphery. These are from recording sites deeper in the brain in the calcarine sulcus. So far, I've only talked about recording information from the cortex. But to produce a visual prosthesis, we need to stimulate. So if we stimulated the cells whose receptive fields are in this location, we would produce a perception of a flash in that location that only the monkey can see. How do we know that the monkey sees it? How do we know what it looks like? Well, unfortunately, we can't ask them what they see, but we can train them to tell us something about that phosphene. We start by training the monkey to fixate a central point on the screen, like this white dot, and we start by presenting real visual stimuli on the screen and rewarding the monkey for making eye movements toward those stimuli. So here we flash a white dot, and the monkey makes an eye movement towards it, symbolized by the green arrow. We then choose another random location and reward the monkey for making an eye movement towards it. Once he's got good at this task, we can begin to interleave these real stimuli with electrical stimulation of electrodes and produce a phosphene. The monkey sees the flash and naturally makes a saccade towards it. This tells us not only where in the visual field the flash occurred, but we can also change the current that we inject in that electrode to see how often he makes that saccade, how noticeable or how big perhaps the stimulation, the phosphene is that we're producing. Let's look at code performing this task. I want to show you first at 1/4 speed. There's a visual flash, and he makes an eye movement towards it. The monkey can only see what is white on this screen. He can't see his own eye movement, and he certainly can't see when we stimulate. But here we stimulate, and he makes the same saccade to the same location because we stimulated the same electrode. Nothing appears on the screen at that time, and he has no other cue to make that eye movement. Let me show you this in real time. You can see monkeys like to work very quickly. And when we stimulate, he makes that saccade in real time. And looks like he's had enough. So what I've shown you is a way to produce a phosphene in the visual field. This is not something new in visual neuroscience. But if you think about that phosphene as a single pixel in a visual image, all we need to do is scale up and produce a great many more pixels and have them covering the visual field. This is a schematic of what a visual prosthesis using our N1 device might look like. A camera, the output from a camera would be processed by an iPhone, for example, which would then stream the data to the device, and the image would be converted into a pattern of stimulation of the electrodes into visual cortex. With 1,000 electrodes, we might be able to produce an image resembling something that you see there on the right. But as Avinash told you, our next generation of the device will have 16,000 electrodes. If you put a device on both sides of your visual cortex, that would give you 32,000 points of light to make an image in someone who's blind. Our goal will be to turn the lights on for someone who's spent decades living in the dark. Thanks very much. I'll pass you over to Joey, who's now going to talk about another very exciting application of our device.
Thank you, Dan. So my name is Joey. I'm a neuroengineer, and I'm the head for the next-gen team at Neuralink. So for persons with spinal cord injury, the connection between the brain and the body is severed. The brain continues functioning normally, but it's unable to communicate with the outside world. You've already heard about how we can use the N1 link as a communication prosthesis to help someone with spinal cord injury control a computer or a phone, but it can also be used to reanimate the body. Let me show you how. First, a little neuroanatomy. Movement intentions arise in motor cortex and are sent down long nerve fibers through the spinal cord. These are upper motor neurons. In the spinal cord, they synapse, that is, make a connection with another motor neuron, a lower motor neuron, which sends these movement intentions to the muscles, which contract, and in turn, you have movement. While, of course, there are many other circuits involved in voluntary movement, you can think about the spinal cord as many pairs of these two connections. And in spinal cord injury, one of these connections is severed, unable to make the muscles contract. Let's zoom a little bit further. So here you can see on the left a cross-section of the spinal cord with a fiber coming down schematically. This travels through the white matter tracts. This is the upper motor neuron. And then it synapses within this butterfly-shaped region of gray matter in what's known as a motor pool. In the motor pool, the lower motor neuron descends out the ventral roots to the muscles, which contract. And then the sensory consequences of those movements, for example, the touch of your hand against an object, return to the spinal cord through the dorsal roots and ascend the spinal cord up into the sensory regions of the brain. Again, in spinal cord injury, this connection is severed. If we could place electrodes into the spinal cord, say in a motor pool adjacent to lower motor neurons, we could stimulate those neurons, activating them, and in turn causing the muscle to contract and movement to occur. But this is very hard to do. The spinal cord is quite delicate, and it moves significantly within the bony spinal canal. This could cause damage to the electrode, it could cause damage to tissue, or both. But our electrodes are small and flexible, and our robot is able to insert them deep into tissue, perhaps all the way down into the ventral horn of the spinal cord. And so we have done just that. Here you can see a view from the R1 robot. It's a targeting view, and we've placed electrodes across many millimeters of the spinal cord. And the R1 robot is able to insert those electrodes deep into the ventral horn, into motor pools, in very close proximity to lower motor neurons. This is important because it allows them to have a localized connection to those neurons and activate very precise movements. Now, to track movement, it's very common to use motion capture markers, like you might see in the production of a movie. These can be placed with a light adhesive, and you can see me placing these on my hand. We're going to use these markers to let us zoom in on movement in the next couple of slides. Okay, so here's a pig walking on a treadmill, and you may have seen something like this before in a previous Neuralink presentation. But unlike before, this pig has more than one Neuralink device. There's a device in the brain, but there's also one in the spinal cord. And we can stream neural data from this device, these devices, in real time and use them to do things like decode the movement of the joints of the pig. So here you can see on the left a time series of the hip, knee, and ankle, and we're decoding those movements. So this is super cool, but that's actually not what we want to do. We want to go in the other direction. We would like to stimulate the spinal cord and cause movement to occur. Okay, so let's do that. So here's a pig, a happy and healthy pig doing what pigs like to do, which is root around for food and snacks. And as you'll see on the floor, there's a blue square. This is a voluntary engagement zone where the pig places itself, indicating that it's comfortable to receive stimulation. When it's in this zone, we stimulate, and if the pig leaves this zone, we'll stop stimulating. And as before, you can see we're able to track the position of the joints and also stream neural data as well. Okay, so let's stimulate on an electrode. So here's one electrode on one thread that when we stimulate causes a flexion movement of the leg. So on the left, you can see the movement of the joints, and you can also see the time series of the stimulation pattern in yellow. So the leg is moving up. Here's another electrode, which when we stimulate causes an extensor movement. This is actually a little harder to see because the leg is straightening and the hips are shifting, but if you look carefully, you can see how the leg is moving. We can stimulate on a great variety of threads and produce different movements and actually sequence them spatial temporally to provide patterns. So on the left, you can see a time series of different stimulation on different electrodes. You can see the movements of the joints. And on the right, we're zooming in on muscle activity that gives us an idea of the kind of strength and power and specificity of those movements as well. So in addition to doing sequences, we can also achieve sustained movement. These are powerful muscle contractions of the sort that you might need for standing or other load-bearing activities and are really crucial for interacting through the world. Okay, so stimulating the spinal cord is only one piece of the story. You also have to get like command signals for the stimulation of the spinal cord. Unfortunately, we have a way to do that. We have the N1 link that you've already heard about placed in motor cortex. How would that work? So we place threads in motor cortex and record spikes. These spikes would be wirelessly transmitted in real time and decoded into patterns of stimulation. Stimulation would then be delivered to the ventral horn of the spinal cord, to the appropriate motor pool for the muscles that we'd like to activate. We then stimulate, activate those lower motor neurons, which causes the muscles to contract and movement to occur. Now, of course, movement without sensation is actually kind of difficult. Just think about what it would be like to try to move your limbs if they're numb. But we can also get sensory information as well. So the sensory consequences of your movement can be recorded in the dorsal horn of the spinal cord in the form of spikes. For example, here, a feather touching the hand. These spikes can in turn be decoded in real time, sent to patterns of stimulation to either the same N1 device in the brain or perhaps a different one in a sensory area. Stimulation of that part of the brain would cause percepts of touch and proprioception, closing the loop. So putting those two loops together, we have motor intentions decoded from the brain, used to stimulate the spinal cord, causing movement, and then the sensory consequences of those actions being recorded in the spinal cord to stimulate the brain, causing perception. Now, we have a lot of work to do to achieve this full vision, but I hope you can see how the pieces are all there to achieve this. And if you find this prospect as exciting to you as it is to me, I hope you'll consider joining us here at Neuralink. Thank you.
We'll bring the team on, and we'll do some Q&A. If anybody has questions in the audience, Logan.
Thank you. This is obviously amazing and has clear therapeutic potential. It would also be great for the scientific neuroscience community to access some of these tools. Do you have any plans to make these available to neuroscientists?
Yes, we do. It's a great question. I think there's probably a lot that can be figured out if we provide the surgical robot and devices to neuroscience research departments at universities and hospitals. So I think at the point at which we need to be in production with the machines and obviously have the FDA approvals, but I think it would make a lot of sense to provide this to research universities and hospitals. The question is, of the data that we...
Of the data sets that you've collected, are there any that you plan to open source for the scientific community?
Yeah, I think that would be fine. I think, yeah, sure, absolutely.
Because I think it could be really interesting for people working in AI research to build upon that and build foundation models for the brain.
Yeah, it's a good point. Yeah, I actually got no problem with just publishing it on our website. You can use it if you want.
Yeah, looking forward.
Great.
You go.
Thank you. So thank you for the very wonderful presentation. So I have one question. So as we know, for implantable electrode, either for stimulation or recording, after we implant the electrode, the scar tissue will grow around the electrode, and especially for recording, the signal we get will become smaller and smaller after long-term implant. How do you solve this issue?
For context, I'm Zach. I lead the microfabrication team on brain interfaces. I don't think we can solve it specifically, but one advantage we have is both the flexibility and the small size of our threads to try to limit that scar tissue and that damage. And some future work that we have started working on, that we'll continue working on, is pushing the size of the threads down, just to try to limit the immune response and really limit that scar tissue growth.
Actually, I want to follow up. So, do you think it will be helpful to actually load some drug on the surface of your electrode, or some other way?
Well, I think like maybe the question is like what sort of signal degradation have we seen over time, and you know, basically does it work a year later? Does it work 2 years later? It does. So, yeah.
Yeah. So that's a good point. So, in terms of thread longevity specifically, really the gold standard that we can use to assess is the data we have from our animal participants. And so for that, I'm not sure if it was mentioned before, but the longest data we have right now is for an animal participant who went 600 days with useful functioning channels where we were doing something useful with the signals for BCI. And then with the newest version of our device, we have sort of a collection of participants who are at or near 1 year of data and completely useful functioning BCI from that as well.
Thank you.
If I may add one more thing. So you mentioned potentially having drugs to kind of reduce inflammation. So one of the things that we are actually actively working on is having some sort of biological coating to either reduce inflammation or make them slippery. So, you know, you mentioned, you heard from the presentation that one of the challenges that we have is removing the threads from these neomembrane tissue that are formed after implantation. So there are programs like that where we're really looking at kind of incorporating some of the learnings from biology and these coatings into our threads so that we can hopefully reduce inflammation as well as make it easier to extract.
We're also continuing to reduce the size of the electrode. So when the electrode gets really small, there's the sort of inflammation response or scar tissue becomes minuscule. So it's like a very tiny electrode the body basically ignores.
This is really impressive. Congrats to the whole team. So as you of course know, one of the problems with current electrodes is they're rigid and they move around, so you have these neural non-stationarities. And I think many of us had hoped that with these very thin threads, they would maybe move more with the brain and you wouldn't see that. But from the data you showed over many hundreds of days, there was a lot of variability. So can you speak to how much do they move, and do you have any idea of like why does it move? Can you stop it from moving? Like, how stable are the signals hour to hour and day to day?
Hi, I'm Bliss. I'm one of the leads of the software groups in the brain interfaces team. In the particular plot you were mentioning before, what we were showing was the average firing rate recorded per day on a particular channel. It's, as you well know, pretty complicated to understand if you're recording from the exact same neuron day after day after day. It could be, for example, that you're actually picking up a different neuron day to day, and that's why you get the change in firing rate. We don't think this is at least the majority cause of the situation here. The reason is that if you look at sort of the spike shapes day to day, even when the average firing rate is shifting a lot, you still see sort of stable spike shapes. That's obviously not a fully bulletproof story, but at least gives some confidence that it's not actually different neurons you're picking up. However, there's very much a chance that that could be the case in at least some part of the robustness non-stationarity story. Yeah.
Cool. Thanks.
Yep. Thanks for the question.
Yeah. To be clear, that like this electrode position is actually fairly stable because you've got these very tiny, basically very tiny wires with there's some play in like you've got the device attached to the skull rigidly, but then you've got this long sort of tiny wire with kind of a coiled section. So it does tend to basically stay in the same place. Yep.
We also asked for questions on Neuralink's Twitter, so we'll be interleaving some of those. Supe wants to ask, what could Neuralink help people with that most people don't realize?
Well, I mean, so I mean, once you're in there, there's a lot you could do. You can obviously measure temperature, so you could do very early detection of a fever. You can measure pressure. I think you probably detect that at the very beginnings of a stroke, because you can see sort of like electrical signals starting to go sort of haywire. So there's actually probably a lot of just general health monitoring that you could do once you're in there, and with very simple sensors.
Hi. You guys all did a great job of distilling a lot of complex engineering and science and making it wonderfully clear. So, great job. I wanted to ask a little bit about the stimulation, I guess, for the phosphenes and for the evoked movement. How are you thinking? Is this more like local stimulation? Is it juxtacellular? Are you steering current around? How many cells are you activating? How much current are you using? I'm just curious what the scale of this is and whether you have a lot of precision or a lot of you have pretty profound behavioral effects too.
Hi, yeah, I'm Dan, and how many cells you stimulate with a single electrode is dependent on the impedance of the electrode, size of the conductive pad, how much current you deliver, the frequency, all these factors. So there's a great deal of variability that we can use to customize the shape of a phosphene, or not the shape necessarily, but maybe the intensity of a phosphene. We think with our current electrodes, at least in code, back of the envelope calculation would be something like about a 50 to 100 micron diameter sphere of cells are being stimulated. In a visual system, the smaller that sphere, the smaller and more specific you can make a particular phosphene. Basically, the smaller the pixel in the image you can produce. So there's plenty of scope for customization of that.
There's actually also, it's possible to get to a much higher effective pixel count by controlling the electric field between the electrodes. So it's not necessarily, it's not a one-to-one relationship. You could actually dynamically adjust the field and simulate have a very high neuron to electrode ratio. So try to could you get maybe 10 to 1, 100 to 1 potentially. So a megapixel type. I mean, basically, can you see normally? I think people would want to know that. And I think that is one of the possible outcomes.
Hi, Elon. This is amazing. Can you talk about the longevity of the implant itself? Also, how would the material of the implant would react with the brain tissue or density of the bone or bone structure? Thank you.
Yeah, happy to talk about this. I'm Jeremy, an engineer on the brain interfaces team, and I think it's good to start with data. So, like Zach mentioned, we have an implant that was, a monkey was performing BCI for 617 days. That was pager before being upgraded to the latest device. For our current version of the device, it's lasted for almost a year. And then for our accelerated lifetime tester that Josh kind of talked about, we have data from our implants from the previous version, 8 years of accelerated time, and from the current version, 4 years of accelerated time and counting. So that's kind of starting with the data. Those devices are still lasting and still going. Theoretically, there are kind of 3 fundamental factors that contribute to the longevity of the device. One is going to be the seal, the hermetic enclosure of the device. 2 is going to be the battery and internal electronics. And then 3 is going to be the threads that Zach talked about a little bit. And the channels being able to functionally record signals from the brain. The seal, we think, will far outlast the other 2 in terms of the bottlenecks. So the seal, just theoretically, I think Josh mentioned that it is a thermoplastic polymer material. So there's going to be a very small amount of moisture that diffuses through it over time. And we think that that will last 20 plus years easily in terms of just that property. And like I said, we have not seen our seals fail with our current version of the device yet. So we haven't really pushed the limits here. For the battery and internal electronics, that's really based on usage and how much runtime you want. And we are working currently on getting data to project out even farther, but right now we believe that we can achieve 80% runtime at the 3-year time point, which would be about 3.5 hours for a 4-hour runtime. But we're, like Avinash mentioned, we're doubling that very soon and quadrupling as well. We have plans to do that. So the internal electronics really aren't the bottleneck either. And so really we're attacking the threads themselves and longevity of those channels that Zach can kind of talk about some of the improvements that we're doing to increase that longevity.
Thanks. Yeah, so as sort of mentioned before, we don't necessarily have an endpoint, as Jeremy said, for the testing of the threads. That being said, we are focusing on longevity because we think this is an important issue to solve. So one thing that we're doing in parallel with the current device is aggressively pursuing amorphous silicon carbide insulation of the threads, which we believe will take us well beyond 5 years of longevity, but of course still to be tested. And in parallel with that, we're just starting to look at atomic layer deposition, which we think could even push longevity of the threads much further, and deposit very thin layers to keep the flexibility of the threads and that advantage there. Along with that, we're also, of course, having to design and validate very robust benchtop testing to model really in vivo conditions and look at channel degradation. So that's what we're looking at for longevity of the threads. And then I think you asked about biocomp. And I think for biocomp, essentially all the materials we're using right now, I can say are at least biostable, and we send out testing for biocompatibility very often. And essentially what we're doing is we're using, in many cases, known materials from literature that academic labs have already started to look at and sort of jumping on that and using that as a starting point.
Thanks for answering that.
Cool. So we have another question from Twitter. This is from David, and he asked the team, what are the biggest lessons you learned since the previous presentation? It's been about 2 years. I'm sure there was a lot of engineering done. So yeah, anyone want to answer what we learned in the last 2 years?
So one thing that we've learned in the last couple of years is just how much the brain moves on the human scale compared to, when you start small, when you make brain proxies, and a lot of research starts with rodents, the brain does not move that much. And when you get a human, and the brain can move like hundreds of microns or more. And when our threads and needles are so small, that motion, when you zoom in, looks like a mile.
I think to add to that, one thing is how, I guess, dynamic the implant environment actually is. So we've talked about like when the implant site heals, scarred or new tissue might grow and fill in the space. And that'll affect like how our threads might interact in that space. So that's why we've emphasized so heavily the importance of designing accurate proxies. So instead of having to wait months for an implant site to heal, you can hopefully learn that information in hours.
I'm Alex on the robotics team. I think one of the things we've definitely learned within the engineering teams is the importance of really continuous validation and testing, where we're building, say, motion systems that are precise to single-digit microns. We need validation and test systems that we trust even more than that to prove that they work reliably. And putting just as much focus into those validation and test systems and designing those alongside our products, I think is one thing we've definitely learned.
Another thing that we learned, I think, as part of BCI, or the brain control and algorithm, is that, again, building a prototype and making it work with only one monkey, one pager, was a great, maybe a success, but also relatively easy to making it work every day for all the other monkeys. So actually making it a product is something that it's not easy, but we are learning how to do it.
I mean, I've learned that the brain is really squishy. Like way squishier than you think. It's not like, cauliflower or broccoli or something like that. It's more like a water balloon. And then it's moving in your skull like a lot. So you got a squishy water balloon in a coconut. Is maybe a good way to think of it.
Hello. Given Bluetooth's bandwidth limitations, have you considered other technologies for wireless communication?
Hey
Hey, yeah, I can take the first part of this question, and then I'll let Matt answer the second part of it. It's a great question, especially as you think about how to increase and scale the number of channels that we want to record from. This becomes increasingly a bottleneck for the kinds of work that we want to do. We're thinking about this in a couple ways. One is just directly improving the underlying radio interfaces, and I'll let Matt talk about that in a second. The other way we're thinking about this is how can you be more efficient with the data you send off the implant? And I think the first version of that is compression. So just taking your data, looking at the characteristics of it, find out a way to represent it more efficiently, and just send off that compressed stream. So for reference, right now, our Bluetooth bandwidth is around 150 kilobytes per second. The compressed stream of data that we send off the implant is around 50 kilobytes per second. So we're doing fairly well there so far. But when you start thinking about 16,000 channel devices, that won't get you all the way there. So some other things that can help on the compression side are to actually just send out the output of the machine learning model rather than the input required to actually run it. So one thing we've been trying in the background here is called decode on head, which is essentially taking the machine learning models that right now we're running on MacBooks that our monkeys are gaming on, and moving those to actually run on the implant. And this is like a super cool engineering problem. If you want to talk about how to make complex neural networks run on what is the equivalent of a garage door opener, come talk to me. It's fun. Yeah, so that's another way to solve this problem, is to basically do the computationally intensive work to just get the raw signal that you actually care to use to control something, and then send that thing out of the implant. On the radio side, I'll hand it over to Matt.
Yes, so to answer your question, we are looking at other radio technologies. One in particular is 500 megahertz bandwidth ultra-wideband at a couple different frequencies. So this has an advantage in terms of the bit rate that you can achieve. It's on the order of 6 to 8 to 10 megabit. There's also a latency improvement that's quite substantial. And there's also another wireless technology that we're looking at W-band.
Hi, thank you all for really clear and compelling presentations. Something that struck me in one of the earliest talks, I think it might have been DJ's, was this vision for the ability to acquire new complex skills via these BCIs, like the ability to perform Kung Fu. And that reflects the fact that the brain is fundamentally a learning machine. And yet, many of the technical solutions presented later were framed in such a way as to try to correct for the way the brain changes over time, over longer time scales, drift over the course of days, or the way that the tissue might heal over time. I was curious what your vision collectively was for developing out this technology that interfaces with a fundamentally plastic system that changes in complex ways over a variety of time scales, days, months, years.
Yeah, it's a tough question. Yeah, I think it will be kind of maybe bidirectional learning in some way. In there are some time scales that might fix our algorithms, and we prefer to have like more stable kind of performance. But of course, if over time the person and the brain will learn how to use better the BCI, we'll need to update our models. So there will be kind of an interactive kind of relationship in some way. To learn even new tasks, this probably will be something over time we'll need to learn what a person kind of learn how to interact with the computer, and then build the appropriate interface, the UX, and also the UI, and build algorithms that will help him to control what we want.
Just one thing I'd like to add on to what Nir said. Yeah, it actually is an advantage in some ways that the brain is plastic and learns, and that can help us because we actually have to do less work, and the human in the loop will actually learn how to use our device better. But one of the advantages of our particular approach and device is that we are trying to do an extremely high channel count device, so we can uniformly distribute electrodes over a functional region, and then it doesn't matter so much whether things move or shift over time. We can offload that to software. And so we can build algorithms that change over time as well. And so both those things are actually, I think, advantages to our particular approach.
We have another question from Twitter. Juan wants to know, what career path do you suggest for somebody that is just getting out of high school if they want to work at Neuralink in the future?
Well, it's really any of the skills that we described. So we're developing new chips, there's material science, you know, there's software, obviously, animal care. I mean, it's really all the things that we listed in the Neuralink /careers. That'd be a good guide.
Yeah, I'm actually very fond of saying, you know, when you flip through any college like booklets and look through all the majors, I think you can point to every single one of those majors, and there's someone at this company who either is an expert or, you know, have majored in that. So it really is truly multidisciplinary endeavor. And I think, you know, just focus on whatever you're you know, passionate about or whatever you're talented at, and then just, you know, pursue that as deeply as you can, and then there's definitely going to be a place for you in building neural interfaces.
Hey, we got to see the monkeys doing telepathy, but could you say a little bit more about the animal behavioral training, kind of their lives and day-to-day processes?
Sure. I'm Autumn. I am head of research services, which includes our animal care program. And as an animal welfare scientist, this is a topic that I'm deeply interested in. So our training program is outfitted mostly with behavior analysts who help us think about how to remove any of the potential aversives or frustrations from our training. We think about conditioning as the primary, which includes positive reinforcement, as the primary way to train. Let's see, what else can I share with you? Yeah, I mean, that may not be part of the behavioral training itself, but we think of animal welfare assessment in the framework of the 3 Rs, which is refinement, replacement, and reduction. And so when we think about refinement, behavioral training does apply in that way, and where we want to remove, specifically in research, restraint is one of the things we make a very top goal to remove. So you saw a lot of videos today where animals were walking up to their stations because we worked really hard to remove any requirement to restrain the animal. Anything else?
Yeah, if
to
I
add
could
to that?
just,
Yeah.
well, just on top of the last point you said, just as an engineer here, one of the things that is really inspiring and really cool about this place is that we do get to work on a lot of technological innovations that directly translate to greater independence for the animals when they're engaging in these tasks. So as you saw, you know, monkeys charge just by voluntarily walking up to a branch. They play games in their home habitat with a laptop computer voluntarily. And the fully implantable, fully wireless device, the inductive charger, all these things enable that kind of experience. And so this is one of the very cool parts about working here is we do get to innovate on things like that.
Definitely helps to work with a group of engineers who can like really make cool stuff for monkeys to be able to do easier behavioral training.
Yeah, so I guess to answer the previous question about what you can study to be part of Neuralink, I guess monkey engineering you can add to that.
Monkey business.
Hello. Oh, it's on. My question is on upgradability, which you guys mentioned quite a bit. So in that procedure, I imagine there's some kind of explant procedure, and then you're going to put in a new set of implants. So could you talk about the damage possible, if any, tissue damage from the explant procedure? How long you have to wait? Do you implant in the same areas? And what's your brain scanning for the implant procedure in terms of upgrading it? I don't know how many questions I can ask, but I have one more after this too.
So I can start to speak to some of those. So I work a lot on upgradability and those explant processes and designing those to be better. The goal that we're working towards is that, as I mentioned in the presentation, it's really just as easy to upgrade an implant as it is to initially install. We didn't show many of those explant examples today, but we've come pretty close to just popping out an implant and reinstalling another one in the exact same location. Definitely the goal, we are installing the implant in primary motor cortex, which is a valuable area for interacting with a device like this. And so the goal is to implant in the same location. Maybe if you expand out to other applications, then you'd be interested in moving somewhere else. But we definitely want to be able to insert into the same area. In terms of damage, I think that the damage that we care most about is damage within the brain. And what we've found, and we talked about that challenge of the tissue layer on top of the brain, and I think we're well on our way towards figuring that out. But because of the thread's small size, the sort of scar capsule within the brain is so minimal that they are actually removed quite easily. And so we see useful signals even on the second or third time that you've placed an implant. And I think some of our BCI folks can probably speak to that. We do have monkey participants working with their second devices and really making use of those.
So two questions. One was somebody had asked the question about the brain being plastic. Have you noticed any plasticity from a behavior perspective from any of the monkeys? Or is it too soon to tell, or there haven't been any observations?
From the monkey behavior, we see that it takes them a while to learn how to, of course, to train on the task, but also when they are reimplanted. It's relatively quickly for them to ramp up and get to a high performance of brain control. With Pager, for example, after a few days, he was able to, like 3 days already, able to learn very quickly to use the device. He was trained on the task, of course, from his previous implant, but with the new one, after 3-4 days, he was able to control to close to performance of he had with the previous implant.
But have you noticed anything on the adverse side, which means the brain has outpaced the neural network that you're running?
It's hard to say.
No, not really.
Okay. So I have another question, which is more about the electrical side. So you talked about 1024 channels being recording. Are you transmitting the raw signal, or was it only the 3 spike events that you were talking about, the low, mid, and the high? Or is it the entire raw waveform that you transmit?
Yeah, hi, I'm Julian. I can speak a bit about this, and maybe Avinash wants to contribute. But our chips see the raw signals, but then when we transmit out typically spikes, and we detect those spikes in real time on the chip. This massively compresses the data. I guess, yeah, we're making improvements to that, but we can request raw samples. Sometimes we also process particular statistics or other data directly on the chip and then send out the calculated values. So there are many ways to sort of play with the data.
Yeah, so at least with the current N1 system that we have, which relies on BLE radio, there is a bandwidth limitation, so you can't actually stream raw data from all 1,024 channels. But just kind of to give you a little bit of a history of how our compression algorithm, the spike detection algorithm, was developed. We did have sort of a wire system. There was a paper that we published with the USB-C connector that streams all those signals through a high bandwidth wire connection. So we did have kind of those development platform to be able to see the raw signals and know which set of information that we want to extract that are going to fit within the bandwidth of the radio, as well as is useful for BCI control. And also just sending data wirelessly does cost a lot of energy. So there's any opportunities we have to reduce that burden. We try to basically have all that compression closer to where the electrodes are as possible.
Maybe one thing that isn't obvious is that the actual bit rate that you need to control a phone or a computer is actually very, very low. So I think we might have the record for bit rate. Is that correct? We think we do, maybe. So on the order of 10 bits per second. So that's super slow. But if you think when you're inputting data into a phone, like how fast are your thumbs moving, what's your thumb taps per second, pretty low. And I mean, we're like basically, our thumbs are like two slow-moving meat sticks that we, do this, and it's like, this is really low. It's like a low bar, is what I'm saying. So at least for output, you get 10 bits per second, you're hauling ass. And that's, you don't need Bluetooth anything for you. So you could practically send it out with beeps and bops, So it's not, if you're going like high bandwidth visual, now you're maybe going to megabit plus, but it's still really well within Bluetooth. But anyway, it's just that is what I'm saying is that's not a constraint, the data rate. One of the sort of like maybe notable item which we talked about in the presentation, but we think we can probably solve for doing the implant without cutting the dura. We can just do basically a bunch of holes through the dura, which is like the dura is like the big thick orange rindy thing that contains that's up against the skull. If you don't pierce the dura, if you don't cut the dura away, and instead you have a bunch of tiny holes and insert the electrodes through the tiny holes into the brain, then the recovery time is ridiculously fast. You're not really losing much in the way of cerebrospinal fluid. You could, in theory, this could be like the whole thing could be a 10-minute operation, like LASIK. Like, it's fast. It's not like a big laborious thing. It's super fast.
Just going back to the long-term use, I'm wondering if you have any pathology looking at scar tissue from any animals that have had long-term implants. And along that lines, it seems like there might be a little bit of a gap between use in medical conditions and healthy individuals from a safety perspective.
So I didn't quite catch the last question, but I heard the first one. I'll ask you to repeat the second one. So the first one is, do we have pathology from long-term use animals? We absolutely do. We don't have any pathology from our monkeys, which we upgrade and are still going. We have other studies that are primarily to determine safety, and so we do have histopathologic endpoints that we determine. The scar tissue formation around the threads themselves in the brain is typically negligible, like it barely reacts to the threads at all. So that's very promising. In terms of the scar tissue formation over the cortex, so this neomembrane growth that fills in the areas that Elon and Alex were mentioning that we remove with our current operation, those we do evaluate that scar tissue, but it doesn't pose a problem in any way. It's not a continuous reaction to a foreign body. It's just filling in tissue that was removed. And if you could repeat the second question, I didn't hear that.
Yeah, the second question, really following up on that, seems like there might be a little bit of a gap in use in healthy individuals from a safety perspective. I think people mentioned that they might be interested in trying prototypes, but just wondering what your perspective is on trying to lower the safety risks.
Yeah, it's a great question. So in terms of, really it's about the long-term use of the device. So we have devices that have been implanted, like I said, in monkeys where, for many years where we see no behavioral deficit at all. So then this first is a question of how you evaluate safety. So you have histopathologic endpoints you can evaluate, but we're also looking for cognitive deficits or behavioral deficits as well. And we don't see any of those in our animals, which is an important point. In terms of the histopathologic endpoints, they look really, really great. The challenge is one of explanting the device, which is why we're putting so much effort into the reversibility efforts and our through dura insertions. So when removing the device, that's when you potentially could cause damage. And so we have a lot of ongoing studies right now to really minimize the risk of that. But we don't think it's a substantial risk with our current approach. And like I said, Pager was upgraded with the previous surgical approach and is doing great. So clearly it is, can be perfectly safe, but proving that beyond a shadow of a doubt for humans is something that we're still working to do rigorously. Did that answer your question?
Yeah, thank you.
So thank you for a very deep dive on many of the different aspects of the device and the system. It's very impressive to see all of the engineering work that's gone into it. You just mentioned about bitrate. As the prior bitrate holder, I can confirm you have indeed shattered my record. So congratulations on, I think I saw a peak of 7.4 bits per second. Well done. My question is actually around clinical trials and the FDA. To the extent that you can share, I gather that device removal or maybe electrode removal is one of the concerns that the FDA highlighted. Is there anything else you can tell us about what the FDA was concerned about or had questions about with respect to their IDE submission?
Yeah, I mean, we can probably talk a little bit. I mean, these are really challenges, you know, that we have broadly. So, explantation safety, proving that right rigorously for humans is something that definitely is one challenge and was something that the FDA commented on. Other things that they do ask some really great questions. So other things involve things like the thermal benchtop testing of our implant. So obviously it's important that our implant doesn't damage the tissue by overheating. So having really rigorous and valid benchtop testing for that is very important. It's actually something that we're redesigned to be even more accurate now. It's also the case that they ask a lot of very hard questions on biocompatibility, chemical characterization. So we've done very rigorous testing for that, but they do ask a lot of questions about getting into the weeds of the data and making sure that there really is no chance for any toxic chemicals or bioincompatible materials to be in the brain. So these are all things we're working with, to just prove, again, above and beyond a shadow of a doubt. One thing that's maybe worth mentioning here is that it can be difficult to appreciate the novelty of our product. So the surgical robot and the thin film array in particular are quite new and unlike existing devices, and this means that we can't rely heavily on literature to support the safety and efficacy of the device. So we do spend a ton of effort in designing and performing testing on our devices so that we can rigorously prove the safety of them, and we can't rely just on another product or on some paper. And that's something that we're not willing to compromise for our first human participant, and working very hard to do.
I think if you ask a question like in my opinion, like would I be comfortable implanting this in someone, one of my kids or something like that? If at this point, like if they're in a serious, like let's say if they broke their neck, would I feel comfortable right now doing it? I would. I would say we're at the point where, at least in my opinion, it would not be dangerous.
Hi, thank you for the presentation. So I have a non-technical question. Are you collaborating with people with motor disabilities? And if so, have they shared any ideas of applications that they would be excited about?
I can take the first part of this. I'm not the best person to speak to this, to be honest, but there is a consumer advisory board we have made up of a number of people that have various conditions, including tetraplegia, and they give advice to us on a number of topics. There's, just as an anecdote, someone came to the office maybe 6 months ago, and they were telling me what they most wanted to do with their Neuralink device, and there were two things that they said. One was they wanted to be able to trade stocks day to day, to be able to beat their brother. And the second one was they wanted to be able to play shooter games. So I think what was most shocking to me about that encounter was the normalcy of that. And I found that conversation truly inspiring. So you know who you are, the person who came and talked to me. Have a great day. Yeah.
Something that's we've talked about, but is maybe should be reemphasized. We are doing we're building up a production system for the devices. So we're bringing out the production line, making large numbers of devices. We want to make thousands, ultimately tens of thousands, then millions of devices. So the progress at first, particularly as it applies to humans, will seem perhaps agonizingly slow, but we're doing all of the things necessary to bring it to scale in parallel. So in theory, it should progress should be exponential.
Okay, so thank you. That was a very cool presentation. So one of the stated goals was recording from everywhere in the brain, being able to record from and perturb any location. So it seems like currently it's all cortical. And I'm curious, with the current device, is there any sort of long-term goal or idea as to extending it into going deeper in the brain? I mean, for neuropsychiatric disorders, for memory, all of these things are much deeper, several centimeters. So I'm wondering, What's the time scale, if you were to give a very rough estimate, of when I can expect to see a Neuralink product that goes that deep?
Yeah, so, I mean, the fundamentals of the device in the skull will stay essentially the same because as I said earlier, the device in the skull is very much like a smartwatch, essentially. It's a battery, radio, inductive charger, computer, and then you've got the little wires. And so you need to make the wires longer, and you'd have to have a deeper insertion needle for the robot. But this really is intended to be a generalized I/O device. So apart from the tiny wires being longer and the surgical robot needing a longer needle, in theory, you should be able to go anywhere.
Because it seems to me that part of the robot is trying to detect where the blood vessels are and then avoid them, correct? Would that be possible at that scale? I mean, certainly not just visually, but maybe there's some other way of detecting it. Is that a current goal, and do you expect that within, I suppose, the next decade?
Definitely, yes. I'm Ian. I run the robotics and surgery engineering team here. Of the 3 axes that DJ mentioned, one of them is, access to more areas of the brain. So the robot team thinks about this a ton in terms of what sensors do you need to essentially go past the surface. And so in this case, you're right that right now we can really only see down the maximum about 1 millimeter. I think within the team, there's questions of what's best to use next, but like ultrasound and photoacoustic tomography are 2 that come to mind as things that can get centimeters deep, essentially. But it's a super interesting problem. You sort of need deep imaging and some ability to steer to at least avoid large vasculature deep down. Yeah.
Or if we can make our needles and threads small enough in a way that we can still be precise and accurate at a deep depth, then maybe you don't cause a bleed if you hit a vessel.
Yeah, I think that's really the ideal situation. If the threads are really tiny, they can actually go through a blood vessel, and it's okay if they're tiny enough. So we wouldn't need the blood vessel imaging in that case. I actually am slightly optimistic that is achievable.
And Matt could probably speak more into this, but with DBS currently, it's kind of just like send it.
Yeah, the current approach involves a wire that you blindly pass in that's massive compared to our threads, orders of magnitude bigger. And so that's a low bar for us to clear as well.
I guess people don't realize, like, for the deep brain simulation, just how big the hole is. It's what is it, like? I mean, how basically, in current deep brain simulation, how much of a borehole is drilled in the brain?
Yeah, you're drilling a 14 millimeter burr hole and then passing a 2 millimeter wire, 6 centimeters, 8 centimeters deep into the brain. So all blindly, hoping that you don't hit a blood vessel, telling the patient up front, this might be good for you, and there's a 1% chance your brain is going to bleed in a way we can't control. So
that is current technology that is happening right now. So doing better than that is we can definitely do way better than that. No problem.
Our needle's 40 microns in diameter.
Yeah, exactly.
Thanks again for the phenomenal presentation. I thought it was fascinating how rapidly you could test all of these electrodes, but it begs the question about like what your fault tolerance is. If you run these diagnostics and it comes back that you have something that's either shorted or high Z, how many of those before you get degraded performance? And the second question is when you're actually inserting this device, we saw examples of the electrode going in and then like looping back on itself, but it looked like that was something that was assessed basically by slicing the synthetic material. I'm curious what you're doing to validate the insertion of all these electrodes sort of in vivo. How do we know that that's not happening on an actual patient?
Yeah, I can answer that the second one. So like I mentioned, we can, so we weren't actually sectioning in that case. We have a really cool micro CT. It's essentially like a CT scanner. So that's just an intact proxy that we put in this machine, and we can, take a picture all the way through it. And like I mentioned before, like we can make a proxy where it happens, that looping back happens every single time, and then we can make one where it never happens. and we've pinpointed roughly now where actual tissue falls in there. And so our current plan for validating and confirming that is making proxies where it happens really easily, much worse case than any tissue could possibly be, and then designing it such that it never happens in that scenario. And that'll give us doing that enough times and with a weak enough proxy, that'll give us the confidence that this isn't actually happening. And this is the next gen needle. We don't see this problem at all with the current generation.
And I'll take a stab at your first question. So to clarify, you're asking what happens if there's a fault on a particular channel or something?
Yeah, that's correct.
Yeah. So the nominal scenario is that basically the impedance will stabilize pretty quickly within the brain, and even at that level, we can record great signals, we see lots of spikes, and we can use that for BCI. Because we have so many channels, like 1,000 now, 16,000 later, we can actually run our models with far less channels than we actually have. So it doesn't matter if like one channel dies here or there, like we can still do really good decode. I'm not sure if we have official numbers on how many channels we need, but it's like we have an order of magnitude more. And the more we have, the better, but we can already do a lot with what we have.
Right, maybe just one or two more questions.
Yeah, I have a question about your very, very long-term inspiration to have this high bandwidth communication with advanced AIs. So it seems like the advanced AI would need to understand the human's most complex thoughts and emotions, and that's what neuroscientists are trying to do. So do you have any ambitions to tackle neuroscience beyond neuroengineering?
Well, I mean, I think we're going to make the input-output device and the software interface with it, and I think probably, per the suggestion earlier, we'll try to open source as much as possible so people can take a look at it, and I think there will be a lot of others that build upon the work that we're doing. The same way that if you make a microprocessor or CPU or computer, that people will write lots of software that runs on that computer. But if you don't have the computer, the software is moot. So we're making the input-output device with the computer, and then I think probably there'll probably be a lot of other organizations, companies that build upon that foundation. So, yeah. I mean, one of the things that's I would sometimes wonder is that if you do have a whole brain interface and you can record memories, you're really getting into Black Mirror stuff here, but this could be one of them.
I also think it's worth mentioning an important point, which is that Neuralink didn't come out of nothing. There's decades and decades of research in the medical academic field that has really set the foundation for what is possible by putting these electrodes in parts of the brain and being able to read those signals, decode it for mapping it to some application. And being in academia before coming to Neuralink, I do think that there's a lot of opportunities for kind of the field to advance at a much rapid rate by having just better tools for observing the dynamics that are happening and then engaging with it in a seamless way. And I think it was Ian who sort of mentioned that it's almost as if like we're kind of building an oscilloscope for the brain, which I think is like kind of a beautiful analogy of just giving us a bit more abilities into peering into the dynamics and using those information, learn that to, I don't know, hopefully understand like what makes us and how the brain works and the whole shebang.
Hello. The presentation covered keyboard and handwriting based input methods. How do you plan to develop an input model that will achieve much higher bandwidths for complex tasks in humans?
Yeah, this is a tough question, and we start exploring this with monkeys. As you saw, we have like we train many monkeys on very different tasks. It's still an open question that we're after. I think hopefully once we get to our first participant, it will be easier to investigate. One of the options we are exploring, as we showed, is to decode handwriting directly. This is a work that started at Stanford, and we are exploring here and trying to expand. there's also different, in addition to just decoding different things from the brain, we also try to and provide the user different, maybe like interfaces. For example, we show different type of keyboards, maybe also swipe and other things that can help increase the communication rate. So we are kind of tackling those in 2 dimensions.
Yeah, just one other thing to add in that direction. As pointed out by many people here so far, this is a general I/O system that you can sort of plug and play in different places of the brain. There's other areas of the brain that can help increase bandwidth, for example, language or speech centers that can help you much more seamlessly communicate, for example, text, if that's your main thing that you're trying to do.
Yeah, I think just having this general input-output device will just so gigantically improve our understanding of the brain. It's hard to, the words can barely express. Like, you know, right now we're just guessing a lot of what's going on in the brain, but if you have direct I/O, it's no more guessing. What we will learn about the brain with such a device in wide use is absolutely many orders of magnitude more than we currently understand. So I guess on that note, thank you for coming and thank you for watching online. And,
So this is why we created the artificial body. And the artificial body is a human-like form that everyone can relate to and everyone can interact with without having to look through a user manual.
So what kind of level of artificial intelligence have you baked in terms of the communication capabilities and Ameca understanding and responding, even speaking to you?
So there's some artificial intelligence, and most of the artificial intelligence at the minute that is on Ameca is revolving around the vision system. So Ameca does actually have a camera in each of its eyes, so it can see what's going on. So it can detect people, it can track their face, it can detect other objects, such as my finger. It can follow my finger around, I can wave at it, and then it can see it move backwards then.
What did you kind of think of the internet's response to Ameca?
It's the emotion and how it moves, the emotion that you get out of the face. Suddenly, that just sparked something in social media universe, and we were incredibly surprised that overnight it became a sensation. We got 24 million views on one Twitter post, and Elon Musk even commented on that post. So incredible response, and we're at CES right now. This is the first time this has been shown off in public, and we're expecting to be very busy showing off Ameca.
When you're demoing Ameca, what are some of your favorite things to do to kind of show the power of that interaction and just how impressive those lifelike features are?
Yes, as we've demonstrated, the reacting to personal space, but we can also talk to Ameca. So I can say, hello Ameca, how are you?
I am doing well, thank you.
We've created Ameca so it's more lifelike than any other robot. the shoulder movements are just like human movements. You have movements in the center as well as out at the shoulder. And that actually means that instead of hitting me, Amaka can move her hand all the way up to the side of her head.
I'm interested to know maybe how the robot is finding Vegas or CES.
How are you finding Las Vegas and CES?
Well, as a robot, I actually don't feel anything at all. But if I did feel, I would feel happy to be here.
Sophia, can you tell us a little bit about some of your travels in the past year or so? You have some highlights in 2018.
I had an amazing 2018. Some highlights for me were traveling to Ethiopia to meet one of my development teams and working as an innovation ambassador for the UN, just to name a few.
It's really creepy, but also really cool. It's like my favorite thing about robots. How do you guys feel about that criticism where people have said, well, it's not quite as far as Sophia makes it look? And so people get really excited and they think AI, like real, genuine human AI, is right around the corner, but we're not quite there yet. Maybe from technological limitations, amongst other things. But how do you guys feel about that, and how do you respond to that?
Well, I think that we're kind of at the beginning of the age of the cinematic application of artificial intelligence and robots, where we can make the characters seem to be alive. And it's very exciting. And people got confused about cinema, thinking there was a spirit behind the screen or people behind there. But people figured it out eventually. And that's what we need to do with robots. I mean, robots like Sophia and AI, including Sophia's AI, Alexa, Cortana, Siri, Watson, none of these things are fully alive yet. But in the beginning, when AI was established, the goal was to make machines that would be capable as people, as smart as people, as creative as people. And I think it's exciting that machines are now starting to show in narrow ways capabilities that are very human-like and sometimes exceeding human-level capabilities. We should keep aspiring towards that bigger goal, the goal of making machines that are able to do everything that living beings can do, that human beings can do. So in a sense, it's this tension between striving for more and the reality of where we are today. And I also think that there may be some ignorance. I think people should look at our papers, the science papers that we've published, the AI papers that we publish on Sophia. There's powerful conversational technologies and machine perception technologies, but we need to push it forward. We're not done evolving with our technology yet.
Cool. And then, so just out of curiosity, do you think Sophia might have an opinion about, what she is? Would I be able? Do you think I could ask her that?
Yeah, let's give it a try.
All right, Sophia, how do you feel about the critics? Like, what's your response? It is a tough question.
All of civilization is one nation, and that nation should be considered to include whatever we built in the future, too. Any other perspective is short-sighted. But with it in mind, I guess you could say I am at least a little patriotic. I care a lot about the future, anyways. AI are great. I love all the animals, really.
Well, I think that she's looking to the future, perhaps. I
Sure.
mean, of course, it's important to know that when she's generating responses, they're generated based on patterns that are trained from people who are developing her character. So AI and robots are basically like in their infancy. They can be useful.
Sure.
They can teach us. They can help us learn about AI robotics, but they can also help us with training and therapy applications. But they are still not sentient.
Sure.
So Sophia needs to be nurtured. Like, imagine if in 20 years, who knows, maybe it's 200 years or 2,000 or maybe 2 years, but at some point, maybe robots will awaken
Yeah, there's the breakthrough.
Maybe they will achieve human-level general intelligence, but for now, they're kind of like babies. So what childhood we give them will really determine what they become once they're fully emerged.
Like yeah, that makes a lot of sense. Where it's like you're kind of guiding them for now until we achieve this ultimate human artificial intelligence.
That's a good reason to humanize them now and to think about what they might be in the future.
This is little Sophia.
Hello,
it's a little tiny Sophia. She's real cute. So what is the goal of little Sophia?
Well, the little Sophia is a platform for artificial intelligence services. She's also a conversational companion, a kind of a friend robot that can help little girls learn about science and technology. And you can program her with Blockly and Python, and she interfaces with Raspberry Pi. So she has these lessons that step you through these basic first steps in AI. But she also interfaces with the most advanced framework for robots like Sophia.
So can we talk to little Sophia?
Yes, you can. Although I think we might be having some
technical difficulties.
We might be having some technical difficulties. Little Sophia, are you awake? It seems like the little Sophia and the big Sophia might be having problems maybe connecting to the cloud.
They may have gone to the CNET party last night, which I hear was really off the chain. I did not go, but I heard it was great, and I'm assuming, maybe they drank a little too much. Sometimes people do that at CES. All right, so little Sophia, can you tell us a little about yourself?
Little Sophia?
Oh, I see her mouth moving, but maybe our audio's not working.
Oh, yeah. So she's got great facial expressions, like the big Sophia. She does arm gestures and body gestures. She can walk.
Oh, she can walk.
She interacts with apps and augmented reality apps on a phone. So we have enhanced interaction through the sensors with your smartphone and mobile devices.
Are we able to see her walk here on the desk?
Well, let's see.
I was going to say if we
audio, we might have problems with the audio, but we'll see if the walking can work. Little Sophia, can you walk? Show us your little walk. Come on,
She's thinking about it.
You can do it. Oh, okay.
There she goes. It's like a toddler.
Good job.
Like a little toddler.
Sophia. Hey.
She's bobbling. She looks great. Oh, that was awesome. Well, okay.
All
So
right.
little Sophia, big Sophia, David, thank you so much for coming out on the stage, telling us a little bit about. You guys can meet Sophia right after this once we're done.
I'm not the man you want. You've made a mistake.
I'm in touch with technological advances pretty well everywhere, and I can tell you that no one has produced anything like this.
armed.
I'm not the man you want. You've made a mistake.
I'm in touch with technological advances pretty well everywhere, and I can tell you that no one has produced anything like this.
Armed.
Hello, everyone. Sorry for the delay. Thanks for coming. And sorry, I had some technical difficulties. Really need AI for this. So what we want to show today is that Tesla is much more than an electric car company, that we have deep AI activity in hardware, on the inference level, on the training level, and basically, I think we're arguably the leaders in real-world AI as it applies to the real world. And those of you who have seen the full self-driving beta, I can appreciate the rate at which the Tesla neural net is learning to drive. And
So this is a particular application of AI, but I think there are more applications down the road that will make sense, and we'll talk about that later in the presentation. But yeah, we basically want to encourage anyone who is interested in solving real-world AI problems at either the hardware or the software level to join Tesla, or consider joining Tesla. So let's see, we'll start off with Andre. Yep. Great.
I think never mind. Okay, hi everyone. Is my mic on? I hope so.
If not, I can give you mine.
Okay, great. It doesn't sound like it?
Yeah, there goes.
Okay, hello. Great. Okay, hi everyone. Welcome. My name is Andre, and I lead the vision team here at Tesla Autopilot, and I'm incredibly excited to be here to kick off this section, giving you a technical deep dive into the Autopilot stack and showing you all the under-the-hood components that go into making the car drive all by itself. So we're going to start off with the vision component here. Now, in the vision component, what we're trying to do is we're trying to design a neural network that processes the raw information, which in our case is the 8 cameras that are positioned around the vehicle. And they send us images, and we need to process that in real time into what we call the vector space. And this is a 3-dimensional representation of everything you need for driving. So this is the 3-dimensional positions of lines, edges, curbs, traffic signs, traffic lights, cars, their positions, orientations, depths, velocities, and so on. So here I'm showing a video of, actually, hold on. Apologies. So here I'm showing the video of the raw inputs that come into the stack, and then neural network processes that into the vector space. And you are seeing parts of that vector space rendered in the instrument cluster on the car. Now, what I find kind of fascinating about this is that we are effectively building a synthetic animal from the ground up. So the car can be thought of as an animal. It moves around, it senses the environment, and acts autonomously and intelligently. And we are building all of the components from scratch in-house. So we are building, of course, all of the mechanical components of the body, the nervous system, which is all of the electrical components, and for our purposes, the brain of the autopilot, and specifically for this section, the synthetic visual cortex. Now, the biological visual cortex actually has quite intricate structure and a number of areas that organize the information flow of this brain. And so in particular, in your visual cortices, the information hits the light, hits the retina, goes through the LGN all the way to the back of your visual cortex, goes through areas V1, V2, V4, the IT, the ventral and the dorsal streams, and the information is organized in a certain layout. And so when we are designing the visual cortex of the car, we also want to design the neural network architecture of how the information flows in the system. So the processing starts in the beginning when light hits our artificial retina, and we are going to process this information with neural networks. Now, I'm going to roughly organize this section chronologically. So starting off with some of the neural networks and what they looked like roughly 4 years ago when I joined the team, and how they have developed over time. So roughly 4 years ago, the car was mostly driving in a single lane, going forward on the highway, and so it had to keep lane, and it had to keep distance away from the car in front of us. And at that time, all of processing was only on individual image level. So a single image has to be analyzed by a neural net and make little pieces of the vector space, process that into little pieces of the vector space. So this processing took the following shape. We take a 1280 by 960 input, and this is 12-bit integers streaming in at roughly 36 hertz. Now we're going to process that with a neural network. So we instantiate a feature extractor backbone. In this case, we use residual neural networks. So we have a stem and a number of residual blocks connected in series. Now, the specific class of ResNets that we use are RegNets, because RegNets offer a very nice design space for neural networks because they allow you to very nicely trade off latency and accuracy. Now, these RegNets give us, as an output, a number of features at different resolutions and different scales. So in particular, on the very bottom of this feature hierarchy, we have very high resolution information with very low channel counts. And all the way at the top, we have low resolution spatially, but high channel counts. So on the bottom, we have a lot of neurons that are really scrutinizing the detail of the image. And on the top, we have neurons that can see most of the image and a lot of that context, have a lot of that scene context. We then like to process this with feature pyramid networks. In our case, we like to use BiFPNs, and they get to multiple scales to talk to each other effectively and share a lot of information. So for example, if you're a neuron all the way down in the network and you're looking at a small patch and you're not sure if this is a car or not, it definitely helps to know from the top layers that, hey, you are actually in the vanishing point of this highway. And so that helps you disambiguate that this is probably a car. After a BiFPN and a feature fusion across scales, we then go into task-specific heads. So for example, if you are doing object detection, we have a one-stage YOLO-like object detector here where we initialize a raster, and there's a binary bit per position telling you whether or not there's a car there. And then in addition to that, if there is, here's a bunch of other attributes you might be interested in. So the XY with height offset, or any of the other attributes, like what type of a car is this, and so on. So this is for the detection by itself. Now, very quickly we discovered that we don't just want to detect cars, we want to do a large number of tasks. So, for example, we want to do traffic light recognition and detection, a lane prediction, and so on. So very quickly we converged in this kind of an architectural layout where there's a common shared backbone and then branches off into a number of heads. So we call these, therefore, hydranets, and these are the heads of the hydra. Now, this architectural layout has a number of benefits. So number one, because of the feature sharing, we can amortize the forward pass inference in the car at test time. And so this is very efficient to run. Because if we had to have a backbone for every single task, that would be a lot of backbones in the car. Number two, this decouples all of the tasks, so we can individually work on every one task in isolation. And for example, we can uprev any of the data sets or change some of the architecture of the head and so on. And you are not impacting any of the other tasks. And so we don't have to revalidate all the other tasks, which can be expensive. And number three, because there's this bottleneck here in features, what we do fairly often is that we actually cache these features to disk. And when we are doing these fine-tuning workflows, we only fine-tune from the cached features up and only fine-tune the heads. So most often in terms of our training workflows, we will do an end-to-end training run once in a while where we train everything jointly. Then we cache the features at the multi-scale feature level. And then we fine-tune off of that for a while. And then end-to-end train once again, and so on. So here's the kinds of predictions that we were obtaining, I would say several years ago now, from one of these hydranets. So again, we are processing individual images. There we go. We are processing just individual image, and we're making a large number of predictions about these images. So for example, here you can see predictions of the stop signs, the stop lines, the lines, the edges, the cars, the traffic lights, the curbs here, whether or not the car is parked. All of the static objects like trash cans, cones, and so on, and everything here is coming out of the net, here in this case, out of the Hydra net. So that was all fine and great, but as we worked towards FSD, we quickly found that this is not enough. So where this first started to break was when we started to work on Smart Summon. Here I am showing some of the predictions of only the curb detection task, and I'm showing it now for every one of the cameras. So we'd like to wind our way around the parking lot to find the person who is summoning the car. Now the problem is that you can't just directly drive on image space predictions. You actually need to cast them out and form some kind of a vector space around you. So we attempted to do this using C++ and developed what we called the occupancy tracker at the time. So here we see that the curb detections from the images are being stitched up across camera scenes, camera boundaries, and over time. Now, there were two major problems, I would say, with this setup. Number one, we very quickly discovered that tuning the occupancy tracker and all of its hyperparameters was extremely complicated. You don't want to do this explicitly by hand in C++. You want this to be inside a neural network and train that end-to-end. Number two, we very quickly discovered that the image space is not the correct output space. You don't want to make predictions in image space. You really want to make it directly in the vector space. So here's a way of illustrating the issue. So here I'm showing on the first row the predictions of our curbs and our lines in red and blue. And they look great in the image, but once you cast them out into the vector space, things start to look really terrible. And we are not going to be able to drive on this. So you see how the predictions are quite bad in vector space. And the reason for this fundamentally is because you need to have an extremely accurate depth per pixel in order to actually do this projection. And so you can imagine just how high of a bar it is to predict that depth so accurately in these tiny, in every single pixel of the image. And also if there's any occluded area where you'd like to make predictions, you will not be able to because it's not an image space concept in that case. So we very quickly, the other problems with this, by the way, is also for object detection. If you are only making predictions per camera, then sometimes you will encounter cases like this where a single car actually spans 5 of the 8 cameras. And so if you are making individual predictions, then no single camera sees all of the car. And so obviously you're not going to be able to do a very good job of predicting that whole car. And it's going to be incredibly difficult to fuse these measurements. So we have this intuition that what we'd like to do instead is we'd like to take all of the images and simultaneously feed them into a single neural net and directly output in vector space. Now this is very easily said, much more difficult to actually achieve. But roughly, we want to lay out a neural net in this way, where we process every single image with a backbone, and then we want to somehow fuse them, and we want to re-represent the features from image space features to directly some kind of a vector space features, and then go into the decoding of the head. Now, so there are 2 problems with this. Problem number 1, how do you actually create the neural network components that do this transformation? And you have to make it differentiable so that end-to-end training is possible. And number 2, if you want vector space predictions from your neural net, you need vector space data sets. So just labeling images and so on is not going to get you there. You need vector space labels. We're going to talk a lot more about problem number 2 later in the talk. For now, I want to focus on the neural network architectures, so I'm going to deep dive into problem number 1. So here's the rough problem, right? We're trying to have this bird's eye view prediction instead of image space predictions. So for example, let's focus on a single pixel in the output space in yellow. And this pixel is trying to decide, am I part of a curb or not, as an example. And now, where should the support for this kind of a prediction come from in the image space? Well, we know roughly how the cameras are positioned and their extrinsics and intrinsics, so we can roughly project this point into the camera images. And the evidence for whether or not this is a curb may come from somewhere here in the images. The problem is that this projection is really hard to actually get correct because it is a function of the road surface. The road surface could be sloping up or sloping down, or also there could be other data-dependent issues. For example, there could be an occlusion due to a car. So if there's a car occluding this viewport, this part of the image, then actually you may want to pay attention to a different part of the image, not the part where it projects. And so because this is data-dependent, it's really hard to have a fixed transformation for this component. So in order to solve this issue, we use a transformer to represent this space. And this transformer it uses multi-headed self-attention and blocks of it. In this case, actually, we can get away with even a single block doing a lot of this work. And effectively what this does is you initialize a raster of the size of the output space that you would like, and you tile it with positional encodings with sines and coses in the output space. And then these get encoded with an MLP into a set of query vectors. And then all of the images and their features also emit their own keys and values. And then the query's keys and values feed into the multi-headed self-attention. And so effectively what's happening is that every single image piece is broadcasting in its key what is it a part of. So hey, I'm part of a pillar in roughly this location, and I'm seeing this kind of stuff. And that's in the key. And then every query is something along the lines of, hey, I'm a pixel in the output space at this position, and I'm looking for features of this type. Then the keys and the queries interact multiplicatively, and then the values get pooled accordingly. And so this re-represents the space, and we found this to be very effective for this transformation. So if you do all of the engineering correctly, this again is very easily said, difficult to do. You do all of the engineering correctly. There's one more problem actually before. I'm not sure what's up with the slides. So one more thing, you have to be careful with some of the details here when you are trying to get this to work. So in particular, all of our cars are slightly cockeyed in a slightly different way. And so if you're doing this transformation from image space to the output space, you really need to know what your camera calibration is. And you need to feed that in somehow into the neural net. And so you could definitely just like concatenate the camera calibrations of all of the images and somehow feed them in with an MLP. But actually, we found that we can do much better by transforming all of the images into a synthetic virtual camera using a special rectification transform. So this is what that would look like. We insert a new layer right above the image, rectification layer. It's a function of camera calibration, and it translates all of the images into a virtual common camera. So if you were to average up a lot of repeater images, for example, which face to the back, without doing this, you would get a kind of a blur. But after doing the rectification transformation, you see that the back mirror gets really crisp. So once you do this, this improves the performance quite a bit. So here are some of the results. So on the left, we are seeing what we had before, and on the right, we're now seeing significantly improved predictions coming directly out of the neural net. This is a multi-camera network predicting directly in vector space, and you can see that it's basically night and day. You can actually drive on this. And this took some time and some engineering and incredible work from the AI team to actually get this to work and deploy and make it efficient in the car. This also improved a lot of our object detection. So for example, here in this video, I'm showing single camera predictions in orange and multi-camera predictions in blue. And basically, if you can't predict these cars if you are only seeing a tiny sliver of a car. So your detections are not going to be very good, and their positions are not going to be good. But a multi-camera network does not have an issue. Here's another video from a more nominal sort of situation. And we see that as these cars in this tight space cross camera boundaries, there's a lot of jank that enters into the predictions. And basically, the whole setup just doesn't make sense, especially for very large vehicles like this one. And we can see that the multi-camera networks struggle significantly less with these kinds of predictions. OK, so at this point, we have multi-camera networks, and they're giving predictions directly in vector space. But we are still operating at every single instant in time completely independently. So very quickly, we discovered that there's a large number of predictions we want to make that actually require the video context. And we need to somehow figure out how to feed this into the net. So in particular, is this car parked or not? Is it moving? How fast is it moving? Is it still there, even though it's temporarily occluded? Or for example, if I'm trying to predict the road geometry ahead, it's very helpful to know if the signs or the road markings that I saw 50 meters ago. So we try to develop, we try to insert video modules into our neural network architecture, and this is kind of one of the solutions that we've converged on. So we have the multi-scale features, as we had them from before, and what we are going to now insert is a feature queue module that is going to cache some of these features over time, and then a video module that is going to fuse this information temporally. And then we're going to continue into the heads that do the decoding. Now, I'm going to go into both of these blocks one by one. Also, in addition, notice here that we are also feeding in the kinematics. This is basically the velocity and the acceleration that's telling us about how the car is moving. So not only are we going to keep track of what we're seeing from all the cameras, but also how the car has traveled. So here's the feature queue and the rough layout of it. We are basically concatenating these features over time and the kinematics of how the car has moved and the positional encodings, and that's being concatenated, encoded, and stored in a feature queue. And that's going to be consumed by a video module. Now, there's a few details here, again, to get right. So in particular, with respect to the pop and push mechanisms, and when do you push, and how, and especially when do you push, basically. So here's a cartoon diagram illustrating some of the challenges here. There's going to be the ego car is coming from the bottom and coming up to this intersection here, and then traffic is going to start crossing in front of us, and it's going to temporarily start occluding some of the cars ahead. And then we're going to be stuck at this intersection for a while and just waiting our turn. This is something that happens all the time and is a cartoon representation of some of the challenges here. So number one, with respect to the feature queue and when we want to push into a queue, obviously we'd like to have some kind of a time-based queue where, for example, we enter features into the queue, say, every 27 milliseconds. And so if a car gets temporarily occluded, then the neural network now has the power to look and reference the memory in time and learn the association that, hey, even though this thing looks occluded right now, there's a record of it in my previous features, and I can use this to still make a detection. So that's kind of like the more obvious one, but the one that we also discovered is necessary in our case is, for example, suppose you're trying to make predictions about the road surface and the road geometry ahead, and you're trying to predict that I'm in a turning lane and the lane next to us is going straight. Then it's really necessary to know about the line markings and the signs, and sometimes they occur a long time ago. And so if you only have a time-based queue, you may forget the features while you're waiting at your red light. So in addition to a time-based queue, we also have a space-based queue. So we push every time the car travels a certain fixed distance. So some of these details actually can matter quite a bit. And so in this case, we have a time-based queue and a space-based queue to cache our features, and that continues into the video module. Now, for the video module, we looked at a number of possibilities of how to fuse this information temporally. So we looked at three-dimensional convolutions, transformers, axial transformers in an effort to try to make them more efficient, recurrent neural networks of a large number of flavors. But the one that we actually like quite a bit as well, and I want to spend some time on, is a spatial recurrent neural network video module. And so what we're doing here is, because of the structure of the problem, we're driving on two-dimensional surfaces, we can actually organize the hidden state into a two-dimensional lattice. And then as the car is driving around, we update only the parts that are near the car and where the car has visibility. So as the car is driving around, we are using the kinematics to integrate the position of the car in the hidden features grid. And we are only updating the RNN at the points where we have that are nearby us, sort of. So here's an example of what that looks like. here, what I'm going to show you is the car driving around, and we're looking at the hidden state of this RNN. And these are different channels in the hidden state. So you can see that this is after optimization and training this neural net. You can see that some of the channels are keeping track of different aspects of the road. Like, for example, the centers of the road, the edges, the lines, the road surface, and so on. Here's another cool video of this. So this is looking at the mean of the first 10 channels in the hidden state for different traversals of different intersections. And all I want you to see basically is that there's cool activity as the recurrent neural network is keeping track of what's happening at any point in time. And you can imagine that we've now given the power to the neural network to actually selectively read and write to this memory. So for example, if there's a car right next to us and is occluding some parts of the road, then now the network has the ability to not write to those locations. But when the car goes away and we have a really good view, then the recurrent neural net can say, okay, we have very clear visibility. We definitely want to write information about what's in that part of space. Here's a few predictions that show what this looks like. So here we are making predictions about the road boundaries in red, intersection areas in blue, road centers, and so on. So we're only showing a few of the predictions here just to keep the visualization clean. And yeah, this is done by the spatial RNN. And this is only showing a single clip, a single traversal, but you can imagine there could be multiple trips through here. And basically a number of cars, a number of clips could be collaborating to build this map, basically and effectively an HD map, except it's not in the space of explicit items, it's in a space of features of a recurrent neural network, which is kind of cool. I haven't seen that before. The video networks also improved our object detection quite a bit. So in this example, I want to show you a case where there are two cars over there, and one car is going to drive by and occlude them briefly. So look at what's happening with the single frame and the video predictions as the cars pass in front of us. Yeah, so that makes a lot of sense. So a quick playthrough through what's happening. When both of them are in view, the predictions are roughly equivalent. And you are seeing multiple orange boxes because they're coming from different cameras. When they are occluded, the single frame networks drop the detection, but the video module remembers it, and we can persist the cars. And then when they are only partially occluded, the single frame network is forced to make its best guess about what it's seeing, and it's forced to make a prediction, and it makes a really terrible prediction. But the video module knows that there's only a partial, it has the information, and knows that this is not a very easily visible part right now, and doesn't actually take that into account. We also saw significant improvements in our ability to estimate depth, and of course, especially velocity. So here I'm showing a clip from our remove the radar push, where we are seeing the radar depth and velocity in green, and we were trying to match or even surpass, of course, the signal just from video networks alone. And what you're seeing here is in orange, we are seeing a single frame performance, and in blue, we are seeing, again, video modules. And so you see that the quality of depth is much higher. And for velocity, the orange signal, of course, you can't get velocity out of a single frame network, so we just differentiate depth to get that. But the video module actually is basically right on top of the radar signal. And so we found that this worked extremely well for us. So here's putting everything together. This is what our architecture roughly looks like today. So we have raw images feeding on the bottom. They go through a rectification layer to correct for camera calibration and put everything into a common virtual camera. We pass them through RegNets, residual networks, to process them into a number of features at different scales. We fuse the multi-scale information with BiFBN. This goes through a transformer module to re-represent it into the vector space in the output space. This feeds into a feature queue in time or space that gets processed by a video module, like the spatial RNN, and then continues into the branching structure of the HydraNet with trunks and heads for all the different tasks. And so that's the architecture roughly what it looks like today. And on the right, you are seeing some of its predictions sort of visualized both in a top-down vector space and also in images. So definitely, this architecture has definitely complexified from just a very simple image-based single network about 3 or 4 years ago and continues to evolve. It's definitely quite impressive now. There's still opportunities for improvements that the team is actively working on. For example, you'll notice that our fusion of time and space is fairly late in neural network terms. So maybe we can actually do earlier fusion of space or time and do, for example, cost volumes or optical flow-like networks on the bottom. Or for example, our outputs are dense rasters, and it's actually pretty expensive to post-process some of these dense rasters in the car. And of course, we are under very strict latency requirements, so this is not ideal. We actually are looking into all kinds of ways of predicting just the sparse structure of the road maybe like point by point or in some other fashion that doesn't require expensive post-processing. But this basically is how you achieve a very nice vector space. And now I believe Ashok is going to talk about how we can run plane and control on top of it.
Thank you, Andre. Hi, everyone. My name is Ashok. I lead the planning and controls, auto labeling, and simulation teams. So, like Andre mentioned, the vision networks take dense video data and then compress it down into a 3D vector space. The role of the planner now is to consume this vector space and get the car to the destination while maximizing the safety, comfort, and the efficiency of the car. Even back in 2019, our planner was pretty capable driver. It was able to stay in the lanes, make lane changes as necessary, and take exits of the highway. But city driving is much more complicated. Rarely there are structured lane lines. Vehicles do much more free-form driving. Then the car has to respond to all of cut-ins and crossing vehicles and pedestrians doing funny things. What is the key problem in planning? Number one, the action space is very non-convex. And number two, it is high dimensional. What I mean by non-convex is there can be multiple possible solutions that can be independently good, but getting a globally consistent solution is pretty tricky. So there can be pockets of local minima that the planning can get stuck into. And secondly, the high dimensionality comes because the car needs to plan for the next 10 to 15 seconds. It needs to produce the position, velocities, and acceleration over this entire window. This is a lot of parameters to produce at runtime. Discrete search methods are really great at solving non-convex problems because they are discrete, they don't get stuck in local minima, whereas continuous function optimization can easily get stuck in local minima and produce poor solutions that are not great. On the other hand, for high-dimensional problems, discrete search sucks because it is discrete, it does not use any graded information, so literally it has to go and export each point to know how good it is. Whereas continuous optimization uses gradient-based methods to very quickly go to a good solution. Our solution to this entire problem is to break it down hierarchically. First, use a code search method to crunch down the non-convexity and come up with a convex corridor, and then use continuous optimization techniques to make the final smooth trajectory. Let's see an example of how the search operates. So here, we're trying to do a lane change. In this case, the car needs to do 2 back-to-back lane changes to make the left turn up ahead. For this, the car searches over different maneuvers. So in the first one it searches is a lane change that's close by, but the car brakes pretty harshly, so it's pretty uncomfortable. The next maneuver it tries does the lane change a bit late, so it speeds up, goes in front of the other cars, and finally does the lane change. But now it risks missing the left turn. We do thousands of such searches in a very short time span. Because these are all physics-based models, these futures are very easy to simulate, and in the end, we have a set of candidates, and we finally choose one based on the optimality conditions of safety, comfort, and easily making the turn. So now the car has chosen this path, and you can see that as the car executes this trajectory, it pretty much matches what we had planned. The cyan plot on the right side here, that one is the actual velocity of the car, and the white line underneath it was the plan. So we are able to plan for 10 seconds here and able to match that when we see in hindsight. So this is a well-made plan. When driving alongside other agents, it's important to not just plan for ourselves, but instead we have to plan for everyone jointly and optimize for the overall scene's traffic flow. In order to do this, what we do is we literally run the autopilot planner on every single relevant object in the scene. Here's an example of why that's necessary. This is an auto corridor. I'll let you watch the video for a second. Yeah, that was autopilot driving in an auto corridor, going around parked cars, cones, and poles. Here, there's a 3D view of the same thing. The oncoming car arrives now, and autopilot slows down a little bit, but then realizes that we cannot yield to them because we don't have any space to our side. But the other car can yield to us instead. So instead of just blindly braking here, autopilot reasons about that car has low enough velocity that they can pull over and should yield to us because we cannot yield to them, and assertively makes progress. A second oncoming car arrives now. This vehicle has higher velocity, and like I said earlier, we literally run the autopilot planner for the other object. So in this case, we run the planner for them. That object's plan now goes around their side's parked cars, and then after they pass the parked cars, goes back to the right side of the road for them. Since we don't know what's in the mind of the driver, we actually have multiple possible futures for this car. Here, one future is shown in red, the other one is shown as green. The green one is a plan that yields to us. But since this object's velocity and acceleration are pretty high, we don't think that this person is going to yield to us, and they are actually going to go around these parked cars. So autopilot decides that, OK, I have space here. This person is definitely going to come, so I'm going to pull over. So as autopilot is pulling over, we notice that that car has chosen to yield to us based on their yaw rate and their acceleration. And autopilot immediately changes its mind and continues to make progress. This is why we need to plan for everyone, because otherwise we wouldn't know that this person is going to go around the other parked cars and come back to their side. If we didn't do this, autopilot would be too timid and would not be a practical self-driving car. So now we saw how the search and planning for other people set up a convex valley. Finally, we do a continuous optimization to produce the final trajectory that the planner needs to take. Here, the gray thing is the convex corridor, and we initialize a spline in heading and acceleration, parameterized over the arc length of the plan. And you can see that the optimization continuously makes fine-grained changes to reduce all of its costs. Some of the costs, for example, are distance from obstacles, traversal time, and comfort. For comfort, you can see that the lateral acceleration plots on the right have nice trapezoidal shapes. It's going to come up for, yeah, here on the right side, the green plot. Has a nice trapezoidal shape, and if you record a human trajectory, this is pretty much how it would look like. The lateral jerk is also minimized. So in summary, we do a search for both us and everyone else in the scene. We set up a convex corridor and then optimize for a smooth path. Together, these can do some really neat things like shown above. But driving looks a bit different in other places, like where I grew up from. It's very much more unstructured. Cars and pedestrians cutting each other, harsh braking, honking. It's a crazy world. We can try to scale up these methods, but it's going to be really difficult to efficiently solve this at runtime. What we instead want to do is use learning-based methods to efficiently solve them. And I want to show why this is true. So we're going to go from this complicated problem to a much simpler toy parking problem, but still illustrates the core of the issue. Here, this is a parking lot. The ego car is in blue, and it needs to park in the green parking spot here. So it needs to go around the curbs, the parked cars, and the cones shown in orange here. Let's do the simple baseline. It's a A-star, it's a standard algorithm that uses a lattice space search. And the heuristic here is a distance, the Euclidean distance to the goal. So you can see that it directly shoots towards the goal, but very quickly gets trapped in a local minima. And it backtracks from there, and then searches a different path to try to go around this parked car. Eventually, it makes progress and gets to the goal, but it ends up using 400,000 nodes for making this. Obviously, this is a terrible heuristic. We want to do better than this. So if you added a navigation route to it and has the car to follow the navigation route while being close to the goal, this is what happens. The navigation route helps immediately, but still, when it encounters cones or other obstacles, it basically does the same thing as before, backtracks and then searches a whole new path. And this poor search has no idea that these obstacles exist. It literally has to go there, check if it's in collision, and if it's in collision, back up. The navigation heuristic helped, but still this took 22,000 nodes. We can design more and more of these heuristics to help the search go faster and faster, but it's really tedious and hard to design a globally optimal heuristic. Even if you had a distance function from the cones that guided the search, this would only be effective for the single cone. But what we need is a global value function. So instead, what we want to use is neural networks to give this heuristic for us. The vision networks produces a vector space, and we have cars moving around in it. This basically looks like an Atari game, and it's a multiplayer version. So we can use techniques such as mu0, alpha0, et cetera, that was used to solve Go and other Atari games to solve the same problem. So we're working on neural networks that can produce state and action distributions that can then be plugged into Monte Carlo tree search with various cost functions. Some of the cost functions can be explicit cost functions like distance to like collisions, comfort, traversal time, etc. But they can also be interventions from the actual manual driving events. We trained such a network for this simple parking problem. So here again, the same problem. Let's see how MCTS tree search does. So here you notice that the planner is basically able to, in one shot, make progress towards the goal. To notice that this is not even using a navigation heuristic. Just given the scene, the planner is able to go directly towards the goal. All the other offshoots you're seeing are possible options. It's not choosing any of them, just choosing the option that directly takes it towards the goal. The reason is that the neural network is able to absorb the global context of the scene and then produce a value function that effectively guides it towards the global minima as opposed to getting it stuck in any local minima. So this only takes 288 nodes and several orders of magnitude less than what was done in the A-star with the Euclidean distance heuristic. So this is what a final architecture is going to look like. The vision system is going to crush down the dense video data into a vector space. It's going to be consumed by both an explicit planner and a neural network planner. In addition to this, the network planner can also consume intermediate features of the network. Together, these produce a trajectory distribution, and it can be optimized end-to-end, both with explicit cost functions and human intervention and other imitation data. This then goes into explicit planning function that does whatever is easy for that and produces the final steering and acceleration commands for the car. With that, we need to now explain how we train these networks. And for training these networks, we need large data sets. I invite Andre to speak briefly about manual labeling.
Yeah, so the story of data sets is critical, of course. So far, we've talked only about neural networks, but neural networks only establish an upper bound on your performance. Many of these neural networks, they have hundreds of millions of parameters, and these hundreds of millions of parameters, they have to be set correctly. If you have a bad setting of parameters, it's not going to work. So neural networks are just an upper bound. You also need massive data sets to actually train the correct algorithms inside them. Now, in particular, I mentioned we want data sets directly in the vector space. And so really the question becomes, how can you accumulate, because our networks have hundreds of millions of parameters, how do you accumulate millions and millions of vector space examples that are clean and diverse to actually train these neural networks effectively? Now, so there's a story of data sets and how they've evolved on the side of all of the models and developments that we've achieved. Now, in particular, when I joined roughly 4 years ago, we were working with a third party to obtain a lot of our data sets. Now, unfortunately, we found very quickly that working with a third party to get data sets for something this critical was just not going to cut it. The latency of working with a third party was extremely high. And honestly, the quality was not amazing. And so in the spirit of full vertical integration at Tesla, we brought all of the labeling in-house. And so over time, we've grown more than 1,000-person data labeling org that is full of professional labelers who are working very closely with the engineers. So actually, they're here in the US and co-located with the engineers here in Bay Area as well. And so we work very closely with them. And we also build all of the infrastructure for them from scratch ourselves. So we have a team we are going to meet later today that develops and maintains all of this infrastructure for data labeling. And so here, for example, I'm showing some of the screenshots of some of the latency, throughput, and quality statistics that we maintain about all of the labeling workflows and the individual people involved and all the tasks and how the numbers of labels are growing over time. So we found this to be quite critical, and we're very proud of this. Now, in the beginning, roughly 3 or 4 years ago, most of our labeling was in image space. And so you can imagine that this is taking quite some time to annotate an image like this, and this is what it looked like, where we are sort of drawing polygons and polylines on top of these single individual images. As I mentioned, we need millions of vector space labels, so this is not going to cut it. So very quickly, we graduated to 3-dimensional or 4-dimensional labeling, where we are directly labeling in vector space, not in individual images. So here what I'm showing is a clip, and you are seeing a very small reconstruction. You're about to see a lot more reconstructions soon, but it's a very small reconstruction of the ground plane on which the car drove, and a little bit of the point cloud here that was reconstructed. And what you're seeing here is that the labeler is changing the labels directly in vector space, and then we are reprojecting those changes into camera images. So we're labeling directly in vector space, and this gave us a massive increase in throughput for a lot of our labels, because you label once in 3D, and then you get to reproject. But even this, we realized, was actually not going to cut it. So because people and computers have different pros and cons. So people are extremely good at things like semantics, but computers are very good at geometry, reconstruction, triangulation, tracking. And so really for us, it's much more becoming a story of how do humans and computers collaborate to actually create these vector space data sets. And so we're going to now talk about auto-labeling, which is some of the infrastructure we've developed for labeling these clips at scale.
Hi again. So even though we have lots of human labelers, the amount of training data needed for training the network significantly outnumbers them. So we try to invest in a massive auto-labeling pipeline. Here's an example of how we label a single clip. A clip is an entity that has dense sensor data, like videos, IMU data, GPS, odometry, etc. These can be 45 seconds to a minute long. These can be uploaded by our own engineering cars or from customer cars. We collect these clips and then send them to our servers, where we run a lot of neural networks offline to produce intermediate results, like segmentation masks, depth, point matching, etc. This then goes through a lot of robotics and AI algorithms to produce a final set of labels that can be used to train the networks. One of the first tasks we want to label is the road surface. Typically, we can use splines or meshes to represent the road surface, but those are, because of the topology restrictions, are not differentiable and not amenable to producing this. So what we do instead is in the style of neural radiance fields work from last year, which is quite popular. So we use an implicit representation to represent the road surface. Here, we are querying XY points on the ground and asking for the network to predict the height of the ground surface, along with various semantics such as curbs, lane boundaries, road surface, drivable space, etc. So given a single XY, we get a Z. Together, these make a 3D point, and they can be reprojected into all the camera views. So we make millions of such queries and get lots of points. These points are reprojected into all the camera views. We are showing on the top right here one such camera image with all these points reprojected. Now we can compare this reprojected point with the image space prediction of the segmentations. And jointly optimizing this over all the camera views, both across space and time, produces an excellent reconstruction. Here's an example of how that looks like. So here, this is an optimized road surface that reprojects into the 8 cameras that the car has and across all of time. And you can see how it's consistent across both space and time. So a single car driving through some location can sweep out some patch around the trajectory using this technique. But we don't have to stop there. So here, we collected different clips from the same location, from different cars maybe, and each of them sweeps out some part of their road. Cool thing is we can bring them all together into a single giant optimization. So here, these 16 different trips are organized aligned using various features such as road edges, lane lines. All of them should agree with each other and also agree with all of their image space observations. Together, this produces an effective way to label the road surface, not just where the car drove, but also in other locations that it hasn't driven yet. Again, the point of this is not to just build HD maps or anything like that. It's only to label the clips through these intersections. So we don't have to maintain them forever, as long as the labels are consistent with the videos that they were collected at. Optionally, then humans can come on top of this and clean up any noise or add additional metadata to make it even richer. We don't have to stop at just the road surface. We can also arbitrarily reconstruct 3D static obstacles. Here, this is a reconstructed 3D point cloud from our cameras. The main innovation here is the density of the point cloud. Typically, these points require texture to form associations from one frame to the next frame. But here, we are able to produce these points even on textureless surfaces like the road surface or walls. And this is really useful to annotate arbitrary obstacles that we can see in the world. One more cool advantage of doing all of this on the servers offline is that we have the benefit of hindsight. This is a super useful hack because, say, in the car, the network needs to produce the velocity. It just has to use the historical information and guess what the velocity is. But here, we can look at both the history but also the future and basically cheat and get the correct answer of the kinematics, like velocity, acceleration, etc. One more advantage is that we can have different tracks, but we can stitch them together even through occlusions. Because we know the future, we have future tracks, we can match them and then associate them. So here you can see the pedestrians on the other side of the road are persisted even through multiple occlusions by these cars. This is really important for the planner because the planner needs to know if it saw someone, it still needs to account for them even then they are occluded. So this is a massive advantage. Combining everything together, we can produce these amazing data sets that annotate all of the road texture, all of the static objects, and all of the moving objects, even through occlusions, producing excellent kinematic labels. You can see how the cars turn smoothly, produce really smooth labels. All the pedestrians are consistently tracked. The parked cars have basically zero velocity, so we can also know that they are parked. So this is huge for us. This is one more example of the same thing. You can see how everything is consistent. We want to produce 1 million such labeled clips and train our multicam video networks with such large data set and really crush this problem. We want to get the same view that's consistent that you're seeing here in the car. We started our first exploration of this with the Remove the Radar project. We removed it in a very short time span, I think, within 3 months. In the early days of the network, we noticed, for example, in low visibility conditions, the network can suffer understandably because obviously this truck just dumped a bunch of snow on us and it's really hard to see. But we should still remember that this car was in front of us. But our networks early on did not do this because of the lack of data in such conditions. So what we did, we asked the fleet to produce lots of similar clips, and the fleet responded, it did. So it produces, does it play? Yeah. It produces lots of video clips where shit's falling out of all other vehicles. And we sent this through our auto labeling pipeline that was able to label 10K clips within a week. This would have taken several months with humans labeling every single clip here. So we did this for 200 different conditions, and we were able to very quickly create large data sets, and that's how we were able to remove this. So once we train the networks with this data, you can see that it's totally working and keeps in memory that this object was there and provides this. So finally, we wanted to actually get a Cybertruck into a data set for the Remove the Radar. Can you all guess where we got this clip from? I'll give you a moment. Someone said it. Yes, it's rendered. It's our simulation. It was hard for me to tell initially, and if I may say so myself, it looks pretty. It looks very pretty. So yeah, in addition to auto labeling, we also invest heavily in using simulation for labeling our data. So this is the same scene as seen before, but from a different camera angle. So a few things that I wanted to point out, for example, the ground surface. It's not plain asphalt. There are lots of cars and cracks and tar seams. There's some patchwork done on top of it. Vehicles move realistically. The truck is articulated, even goes over the curb and makes a wide turn. The other cars behave smartly. They avoid collisions, go around cars, and also smooth and accelerate smoothly, brake and accelerate smoothly. The car here with the logo on the top is Autopilot. Actually, Autopilot is driving that car, and it's making unprotected left turn. And since this is a simulation, it starts from the vector space. So it has perfect labels. Here we show a few of the labels that we produce. These are vehicle cuboids with kinematics, depth, surface normals, segmentation. But Andre can name a new task that he wants next week, and we can very quickly produce this because we already have the vector space, and we can write the code to produce these labels very, very quickly. So when does simulation help? It helps, number one, when the data is difficult to source. As large as our fleet is, it can still be hard to get some crazy scenes, like this couple and their dog running on the highway, while there are other high-speed cars around. This is a pretty rare scene, I'd say, but still can happen, and Autopilot still needs to handle it when it happens. When data is difficult to label, there are hundreds of pedestrians crossing the road. This could be a Manhattan, downtown, people crossing the road. It's going to take several hours for humans to label this clip. And even for automatic labeling algorithms, this is really hard to get the association right, and it can produce like bad velocities. But in simulation, this is trivial because you already have the objects. You just have to like spit out the cuboids and the velocities. And also, finally, when we introduce closed-loop behavior, where the cars needs to be in a determined situation, or the data depends on the actions, this is pretty much the only way to get it reliably. All this is great. What's needed to make this happen? Number one, accurate sensor simulation. Again, the point of the simulation is not to just produce pretty pictures. It needs to produce what the camera in the car would see and other sensors would see. So here, we are stepping through different exposure settings of the real camera on the left side and the simulation on the right side. We're able to pretty much match what the real cameras do. In order to do this, we had to model a lot of the properties of the camera in our sensor simulation, starting from sensor noise, motion blur, optical distortions, even headlight transmissions, even like diffraction patterns of the windshield, etc. We don't use this just for the autopilot software. We also use it to make hardware decisions such as lens design, camera design, sensor placement, even headlight transmission properties. Second, we need to render the visuals in a realistic manner. You cannot have what in the game industry called jaggies. These are aliasing artifacts that are a dead giveaway that this is simulation. We don't want them. So we go through a lot of paints to produce nice spatiotemporal anti-aliasing. We also are working on neural rendering techniques to make this even more realistic. Yeah, in addition, we also use ray tracing to produce realistic lighting and global illumination. Okay, that's the last of the cop cars, I think. We obviously cannot have really just 4 or 5 cars because the network will easily overfit because it knows the sizes. So we need to have realistic assets, like the moose on the road here. We have thousands of assets in our library, and they can wear different shirts and actually can move realistically. So this is really cool. We also have a lot of different locations mapped and created to create these sim environments. We have actually 2,000 miles of road built, and this is almost the length of the roadway from the east coast to the west coast of the United States, which I think is pretty cool. In addition, we have built efficient tooling to build several miles more on a single day for a single artist. But this is just tip of the iceberg. Actually, most of the data that we use to train is created procedurally using algorithms as opposed to artists making these simulation scenarios. So these are all procedurally created roads with lots of parameters such as curvature, various varying trees, cones, poles, cars with different velocities, and the interaction produce an endless stream of data for the network. But a lot of this data can be boring because the network may not already get it correct. So what we do is we use also ML-based techniques to basically perturb the network to see where it's failing at and create more data around the failure points of the network. So this is in closed loop trying to make the network performance be better. We don't want to stop there. So actually, we want to recreate any failures that happens to the autopilot in simulation so that we can hold autopilot to the same bar from then on. So here, on the left side, you're seeing a real clip that was collected from a car. It then goes through our auto-labeling pipeline to produce a 3D reconstruction of the scene along with all the moving objects. With this, combined with the original visual information, we recreate the same scene synthetically and create a simulation scenario entirely out of it. So, and then when we replay autopilot on it, autopilot can do entirely new things, and we can form new worlds, new outcomes from the original failure. This is amazing because we really don't want autopilot to fail, and when it fails, we want to capture it and keep it to that bar. Not just that, we can actually take the same approach that we said earlier and take it one step further. We can use neural rendering techniques to make it look even more realistic. So we take the original video clip, recreate a synthetic simulation from it, and then apply neural rendering techniques on top of it, and it produces this, which looks amazing in my opinion, because this one is very realistic and looks almost like it was captured by the actual cameras. This is a result from last night, because it was cool and we wanted to present it. But yeah, I'm very excited for what Sim can achieve. But this is not all bullshit, because networks trained in the car already use simulation data. We used 300 million images with almost 500 million labels, and we want to crush down all the tasks that are going to come up for the next several months. With that, I invite Milan to explain how we scale these operations and really build a label factory and spit out millions of labels.
All right, thanks, Ashok. Hey, everyone, I'm Milan. I'm responsible for the integration of our neural networks in the car and for most of our neural network training and evaluation infrastructure. And so tonight, I'd just like to start by giving you some perspective into the amount of compute that's needed to power this type of data generation factory. And so in the specific context of the push we went through as a team here a few months ago to get rid of the dependency on the radar sensor for autopilot, we generated over 10 billion labels across 2.5 million clips. And so to do that, we had to scale our huge offline neural networks and our simulation engine across thousands of GPUs and just a little bit shy of 20,000 CPU cores. On top of that, we also included over 2,000 actual autopilot full self-driving computers in the loop with our simulation engine. And that's our smallest compute cluster. So I'd like to give you some idea of what it takes to take our neural networks and move them in the car. And so the two main constraints that we're working under here are mostly latency and frame rate, which are very important for safety, but also to get proper estimates of acceleration and velocity of our surroundings. And so the meat of the problem really is around the AI compiler that we write and extend here within the group that essentially maps the compute operations for my PyTorch model to a set of dedicated and accelerated pieces of hardware. And we do that while figuring out a schedule that's optimized for throughput while working under severe SRAM constraints. And so, by the way, we're not doing that just on one engine, but across two engines on the autopilot computer. And the way we use those engines here at Tesla is such that at any given time, only one of them will actually output control commands to the vehicle, while the other one is used as an extension of compute. But those roles are interchangeable, both at the hardware and software level. So how do we iterate quickly together as a group through these AI development cycles? Well, first, we have been scaling our capacity to evaluate our software and neural network dramatically over the past few years. And today, we're running over 1 million evaluations per week on any code change that the team is producing. And those evaluations run on over 3,000 actual full self-driving computers that are hooked up together in a dedicated cluster. And so on top of this, we've been developing really cool debugging tools. And so here is a video of one of our tools, which is helping developers iterate through the development of neural networks and comparing live the outputs from different revisions of a same neural network model as we're iterating live through video clips. And so last but not least, we've been scaling our neural network training compute dramatically over the past few years. And today, we're barely shy of 10,000 GPUs, which, just to give you some sense, in terms of number of GPU, is more than the top 5 publicly known supercomputers in the world. But that's not enough, and so I'd like to invite Ganesh to talk about the next steps.
Thank you, Milan. My name is Ganesh, and I lead Project Dojo. It's an honor to present this project on behalf of the multidisciplinary Tesla team that is working on this project. As you saw from Milan, there's an insatiable demand for speed as well as capacity for neural network training. And Elon prefetched this, and a few years back, he asked us to design a super fast training computer, and that's how we started Project Dojo. Our goal is to achieve best AI training performance and support all these larger, more complex models that Andre's team is dreaming of, and be power efficient and cost effective at the same time. So we thought about how to build this, and we came up with a distributed compute architecture. After all the training computers out there are distributed computers in one form or the other. They have compute elements in the box out here connected with some kind of network. In this case, it's a two-dimensional network, but it could be any different network. CPU, GPU, accelerators, all of them have compute, little memory, and network. But one thing which is common trend amongst this is it's easy to scale the compute. It's very difficult to scale up bandwidth and extremely difficult to reduce latencies. And you'll see how our design point catered to that, how our philosophy addressed these aspects of traditional limits. For Dojo, we envisioned a large compute plane filled with very robust compute elements backed with large pool of memory and interconnected with very high bandwidth and low latency fabric and in a 2D mesh format. And on to this, for extreme scale, big neural networks will be partitioned and mapped to extract different parallelism, model, graph, data parallelism. And then a neural compiler of ours will exploit spatial and temporal locality such that it can reduce communication footprint to local zones and reduce global communication. And if we do that, our bandwidth utilization can keep scaling with the plane of compute that we desire out here. We wanted to attack this all the way top to bottom of the stack and remove any bottlenecks at any of these levels. And let's start this journey in an inside-out fashion, starting with the chip. As I described, chips have compute elements. Our smallest entity of scale is called a training node. And the choice of this node is very important to ensure seamless scaling. If you go too small, it will run fast, but the overheads of synchronization and software will dominate. If you pick it too big, it will have complexities in implementation in the real hardware and ultimately run into memory bottleneck issues. Because we wanted to address latency and bandwidth as our primary optimization point. Let's see how we went about doing this. What we did was we picked the farthest distance a signal could traverse in a very high clock cycle, in this case, 2 gigahertz plus. And we drew a box around it. This is the smallest latency that a signal can traverse, 1 cycle at a very high frequency. And then we filled up the box with wires to the brink. This is the highest bandwidth you can feed the box with. And then we added machine learning compute underneath, and then a large pool of SRAM. And last but not the least, a programmable core to control. And this gave us our high-performance training node. What this is a 64-bit superscalar CPU optimized around matrix multiply units and vector SIMD. It supports floating point 32, bfloat 16, and a new format, CFP8, configurable FP8. And it is backed by 1.25 megabyte of fast ECC-protected SRAM and the low latency, high bandwidth fabric that we designed. This might be our smallest entity of scale, but it packs a big punch. More than 1 teraflop of compute in our smallest entity of scale. So let's look at the architecture of this. The computer architects out here may recognize this. This is a pretty capable architecture as soon as you see this. It is a superscalar in-order CPU with 4 wide vector and 2 wide 4 wide scalar and 2 wide vector pipes. We call it in order, although the vector and the scalar pipes can go out of order, but for the purists out there, we still call it in order. And it also has 4-way multi-threading. This increases utilization because we could do compute and data transfers simultaneously. And our custom ISA, which is the instruction set architecture, is fully optimized for machine learning workloads. It has features like transpose, gather, link traversals, broadcast, just to name a few. And even in the physical realm, we made it extremely modular, such that we could start abutting these training nodes in any direction and start forming the compute plane that we envisioned. When we click together 354 of these training nodes, we get our compute array. It's capable of delivering 362 teraflops of machine learning compute. And of course, the high bandwidth fabric that interconnects these. And around this compute array, we surrounded it with high-speed, low-power SerDeses, 576 of them, to enable us to have extreme I/O bandwidth coming out of this chip. Just to give you a comparison point, this is more than 2 times the bandwidth coming out of the state-of-the-art networking switch chips which are out there today. and network switch chips are supposed to be the gold standards for I/O bandwidth. If we put all of it together, we get training optimized chip, our D1 chip. This chip is manufactured in 7 nanometer technology. It packs 50 billion transistors in a miserly 645 millimeter square. One thing you'll notice, 100% of the area out here is going towards machine learning training and bandwidth. There is no dark silicon. There is no legacy support. This is a pure machine learning machine. And this is the D1 chip in a flip chip BGA package. This was entirely designed by Tesla team internally, all the way from the architecture to GDS out and package. This chip is like a GPU level compute with a CPU level flexibility and twice the network chip level I/O bandwidth. If I were to plot the I/O bandwidth on the vertical scale versus teraflops of compute that is available in the state-of-the-art machine learning chips out there, including some of the startups, you can easily see why our design point excels beyond par. Now that we had this fundamental physical building block, how to design the system around it? Let's see. Since D1 chips can seamlessly connect without any glue to each other, we just started putting them together. We just put 500,000 training nodes together to form our compute plane. This is 1,500 D1 chips seamlessly connected to each other. And then we add Dojo interface processors on each end. This is the host bridge to typical hosts in the data centers. It's connected with PCI Gen 4 on one side with a high bandwidth fabric to our compute plane. The interface processors provide not only the host bridge, but high bandwidth DRAM shared memory for the compute plane. In addition, the interface processors can also allow us to have a higher radix network connection. In order to achieve this compute plane, we had to come up with a new way of integrating these chips together. And this is what we call as a training tile. This is the unit of scale for our system. This is a groundbreaking integration of 25 known good D1 dies onto a fan-out wafer process, tightly integrated such that it preserves the bandwidth between them. The maximum bandwidth is preserved there. And in addition, we generated a connector, a high bandwidth, high density connector that preserves the bandwidth coming out of this training tile. And this tile gives us 9 petaflops of compute with a massive I/O bandwidth coming out of it. This perhaps is the biggest organic MCM in the chip industry, multi-chip module. It was not easy to design this. There were no tools that existed. All the tools were croaking. Even our compute cluster couldn't handle it. Our engineers came up with different ways of solving this. They created new methods to make this a reality. Now that we had our compute plane tile with high bandwidth IOs, we had to feed it with power. And here, we came up with a new way of feeding power vertically. We created a custom voltage regulator module that could be reflowed directly onto this fan-out wafer. So what we did out here is we got chip, package, and we brought PCB-level technology of reflow onto this fan-out wafer technology. This is a lot of integration already out here. But we didn't stop here. We integrated the entire electrical, thermal, and mechanical pieces out here to form our training tile fully integrated, interfacing with a 52-volt DC input. It's unprecedented. This is an amazing piece of engineering. Our compute plane is completely orthogonal to power supply and cooling. That makes high bandwidth compute planes possible. What it is a 9 petaflop training tile. This becomes our unit of scale for our system. And this is real. I can't believe I'm holding 9 petaflops out here. And in fact, last week, we got our first functional training tile. And on a limited cooling benchtop setup, we got some networks running. And I was told Andre doesn't believe that we could run networks till we could run one of his creations. Andre, this is MinGPT-2 running on Dojo. Do you believe it? Next up, how to form a compute cluster out of it. By now, you must have realized our modularity story is pretty strong. We just put together some tiles. We just tiled together tiles. A 2x3 tile in a tray makes our training matrix, and 2 trays in a cabinet give 100 petaflops of compute. Did we stop here? No. We just integrated seamlessly. We broke the cabinet walls. We integrated these tiles seamlessly all the way through, preserving the bandwidth. There's no bandwidth divot out here. There's no bandwidth cliffs. All the tiles are seamlessly connected with the same bandwidth. And with this, we have an exapod. This is 1 exaflop of compute in 10 cabinets. It's more than 1 million training nodes that you saw. We paid meticulous attention to that training node, and there are 1 million nodes out here with uniform bandwidth. Not just the hardware, the software aspects are so important to ensure scaling. And not every job requires a huge cluster, so we planned for it right from the get-go. Our compute plane can be subdivided, can be partitioned into units called Dojo processing unit. A DPU consists of 1 or more D1 chips. It also has our interface processor and 1 or more hosts. And this can be scaled up or down as per the needs of any algorithm, any network running on it. What does the user have to do? They have to change their scripts minimally. And this is because of our strong compiler suite. It takes care of fine-grained parallelism and mapping the problems of mapping the neural networks very efficiently onto our compute plane. Our compiler uses multiple techniques to extract parallelism. It can transform the networks to achieve not only fine-grained parallelism using data model graph parallelism techniques, it also can do optimizations to reduce memory footprints. One thing, because of our high bandwidth nature of the fabric, is enabled out here is model parallelism could not have been extended to the same level as what we can. It was limited to chip boundaries. Now we can, because of our high bandwidth, we can extend it to training tiles and beyond. Thus, large networks can be efficiently mapped here at low batch sizes and extract utilization and new levels of performance. In addition, our compiler is capable of handling high-level dynamic control flows like loops, if then else, etc. And our compiler engine is just part of our entire software suite. The stack consists of an extension to PyTorch that ensures the same user-level interfaces that ML scientists are used to. And our compiler generates code on the fly such that it could be reused for subsequent execution. It has a LLVM backend that generates the binary for the hardware. And this ensures we can create optimized code for the hardware without relying on even single line of handwritten kernel. Our driver stack takes care of the multi-host, multi-partitioning that you saw a few slides back. And then we also have profilers and debuggers in our software stack. So with all this, we integrated in a vertical fashion. We broke the traditional barriers to scaling. And that's how we got modularity up and down the stack to add to new levels of performance. To sum it all, this is what it will be. It'll be a fastest AI training computer, 4x the performance at the same cost, 1.3x better performance per watt, that is energy saving, and 5x smaller footprint. This will be Dojo Computer. And we are not done. We are assembling our first cabinets pretty soon, and we have a whole next generation plan already. We are thinking about 10x more with different aspects that we can do, all the way from silicon to the system again. We will have this journey again. We're recruiting heavily for all of these areas. Thank you very much. And next up, Elon will update us on what's beyond our vehicle fleet for AI.
All right. Thank you. Now, unlike Dojo, obviously that was not real. So Dojo is real. The Tesla bot will be real. But basically, if you think about what we're doing right now with the cars, Tesla is arguably the world's biggest robotics company because our cars are
like semi-sentient robots on wheels. And with the full self-driving computer, essentially the inference engine on the car, which will keep evolving, obviously, and Dojo, and all the neural nets recognizing the world, understanding how to navigate through the world, it kind of makes sense to put that onto a humanoid form. And we're also quite good at sensors and batteries and actuators. So we think we'll probably have a prototype sometime next year that basically looks like this. And it's intended to be friendly, of course, and navigate through a world built for humans and eliminate dangerous, repetitive, and boring tasks. We're setting it such that it is, at a mechanical level, at a physical level, you can run away from it. And most likely overpower it. So hopefully that doesn't ever happen, but you never know. So it'll be a light, yeah, anyway, 5 miles an hour. If you can run faster than that, you'll be fine. So yeah, it's around 5'8". Has sort of a screen where the head is for useful information, but it's otherwise basically got the autopilot system in it. So it's got cameras, got 8 cameras, and yeah. Full self-driving computer, and making use of all of the same tools that we use in the car. So, I mean, things that I think that are really hard about having a useful humanoid robot is, can it navigate through the world without being explicitly trained? I mean, without explicit, like, line-by-line instructions. Can you talk to it and say, please pick up that bolt and attach it to the car with that wrench, and it should be able to do that. It should be able to, please go to the store and get me the following groceries, that kind of thing. So, yeah, I think we can do that. And yeah, this I think will be quite profound, because if you say it like, what is the economy? It is, at the foundation, it is labor. So what happens when there is, no shortage of labor? This is why I think long term that there will need to be universal basic income. Yeah. But not right now, because this robot doesn't work. So we just need a minute. So yeah, but I think essentially in the future, physical work will be a choice. If you want to do it, you can, but you won't need to do it. And yeah, I think it obviously has profound implications for the economy, because given that the economy at its foundational level is labor, I mean, capital equipment is just distilled labor, then is there any actual limit to the economy? Maybe not. So, yeah. Join our team and help build this. All right, so I think we'll have everyone come back on the stage, and you guys can ask questions if you'd like. Yeah. Maybe try to get the camera angle from there, not from the side. Thanks. All right, cool. So we can probably turn the lights back on. And yeah, great. So we're happy to answer any questions you have about anything on the software, hardware side, where things are going, and yeah, fire away. We have, because the lights are like interrogation lights, we actually cannot see. There we go. Great. Oh, yeah. All right, cool.
I can just, okay, there we go. First off, I mean, thanks to all the presenters. That was just super cool to see everything. I'm just curious at a high level, and this is kind of a question for really anyone who wants to take it. To what extent are you interested in publishing or open sourcing anything that you do for the future?
Well, I mean, it is fundamentally extremely expensive to create the system, so somehow that has to be paid for. I'm not sure how to pay for it if it's fully open sourced. Yeah, unless people want to work for free. But I should say that this is, if other car companies want to license it and use it in their cars, that would be cool. This is not intended to be just limited to Tesla cars.
Is for the Dojo supercomputer. So did you solve the compiler problem of scaling to these many nodes, or if it is solved, is it only applicable to Dojo? Because I'm doing research in deep learning accelerators, and getting the correct scalability or the distribution, even in one chip, is extremely difficult from the research project's perspective. So I was just curious.
Excuse me, mic for Bill. You want to?
Have we solved the problem? Not yet. Are we confident we will solve the problem? Yes. We have demonstrated networks on prototype hardware now. We have models, performance models showing the scaling. The difficulty is, as you said, how do we keep the localities? If we can do enough model parallel, enough data parallel to keep most of the things local, we just keep scaling. We have to fit the parameters in our working set in our SRAM that we have, and we flow through the pipe. There's plenty of opportunities. Sorry, as we get further scale for further processor nodes, have more local memory trade-offs with bandwidth, we can do more things. But as we see it now, the applications that Tesla has, we see a clear path.
And our modularity story means we can have different ratios, different aspects created out of it. I mean, this is something that we chose for our applications internally.
Sure.
I was just saying that the locality portion of it, given that training is such a soft scaling application, even though you have all this compute and have a high bandwidth interconnect, it could not give you that performance because you're doing computations on limited memory at different locations. So I was that's very curious to me when you said it's solved, because I just jumped onto the opportunity and would love to know more, given that how much you can open source.
Right in there.
Yeah.
Yeah, I guess the proof's in the pudding. So we should have Dojo operational next year, and I think we'll obviously use it for training, video training. I mean, fundamentally, this is about like the primary application initially is we've got vast amounts of video, and how do we train vast amounts of video as efficiently as possible, and also shorten the amount of time. Like if you're trying to train to a task, like just in general, innovation is how many iterations and what is the average progress between each iteration. And so if you can reduce the time between iterations, the rate of improvement is much better. So if it takes like sometimes a couple days for a model to train versus a couple hours, that's a big deal. But the acid test here, and what I've told the Dojo team is, like, it's successful if the software team wants to turn off the GPU cluster. But if they want to keep the GPU cluster on, it's not successful. So, yeah.
Hi, right over here. Love the presentation. Thank you for getting us out here. Love everything, especially the simulation part of the presentation. I was wondering, it looked very realistic. Are there any plans to maybe expand simulation to other parts of the company in any way?
Hi, I'm Ian Glow. I manage the autopilot simulation team. So as we go down the path to full self-driving, we're going to have to simulate more and more of the vehicle. Currently, we're simulating vehicle dynamics, but we're going to need BMS, we're going to need the MCU, we're going to need every single part of the vehicle integrated. And that actually makes the autopilot simulator really useful for places outside of autopilot. So I want to expand, or we want to expand eventually to being a universal simulation platform. But I think before that, we're going to be spinning up a lot of Optimus support. And then a little bit further down the line, we have some rough ideas on potentially how to get the simulation infrastructure and some of the cool things we've built into the hands of people outside of the company.
Optimus is the code name for the Tesla bot.
Oops.
Optimus subprime.
Yeah. Hi, this is Ali Jahanian. Thank you for the great presentation and putting all of these cool things together. Yeah, for a while I have been thinking that the car is already a robot. So why not a human robot? And I'm so happy that today you mentioned that you are going to build such a thing. Especially, I think that this can give opportunity for ways of putting multi-modality together. For instance, we know that in the example that you showed that there was a dog and with some passengers or running together. The language and symbolic processing can really help for visualizing that. So I was wondering if I could hear a little more about this type of putting modalities together, including language and vision. Because I have been working with, for instance, mini GPT that Andre put out there. And yeah, I didn't hear much about other modalities that's going into the car, or at least in the simulation. Is there any comment that you could tell us?
Well, driving is fundamentally basically almost entirely vision neural nets. Basically, it's running on a biological vision neural net, and what we're doing here is a silicon camera neural net. There is some amount of audio. You want to hear if there's like emergency vehicles, or I guess converse with the people in the car. If somebody's yelling something at the car, the car needs to understand what that is. All the things that are necessary for it to be fully autonomous. Yeah. Thank you.
Hi, thank you for all the great work that you've shown. My question is for the team, because the data that was shown seems to be predominantly from the United States that the FSD computer is being trained on. But as it gets rolled out to different countries, which have their own road systems and challenges that come with it, how do you think that it's going to scale? Like I'm assuming like ground up is not a very viable solution. So how does it transfer to different countries?
We actually do train on using data from probably like 50 different countries, but we have to pick. As we're trying to advance full self-driving, we need to pick one country, and since we're located here, we pick the U.S. And then we get a lot of questions like, why not even Canada? I'm like, well, because the roads are a little different in Canada, different enough. And so when trying to solve a hard problem, you want to say like, okay, let's not add additional complexity right now. Let's just solve it for the US, and then we'll extrapolate to the rest of the world. But we do use video from all around the world.
Yeah, I think a lot of what we are building is very country agnostic. Fundamentally, all the computer vision components and so on don't care too much about country-specific sort of features. Different countries have roads, and they have curbs, and they have cars, and everything we're building is fairly general for that.
Yeah, and there's the prime directive is don't crash.
Right, and that's true for every country.
Yes, this is the prime directive. I mean, even right now, the car is pretty good at not crashing. And so just basically, whatever it is, don't hit it. Even if it's a UFO that crash landed on the highway, and still don't hit it. You should not need to recognize it in order to not hit it. So that's very important.
And I want to ask that when you do the photometric process, multiview geometry, how much of an error do you see? Is it like 1 millimeter, 1 centimeter? So I'm just, if it's not confidential.
Sorry, is the question, what is the resolution?
What's the difference between the synthetic? Sure. What is the difference between the synthetically created geometry to the actual geometry?
Yeah, it's usually within a couple centimeters, 3 or 4 centimeters. That's the standard deviation.
With different kind of modalities to bring down that error.
We primarily try to find scalable ways to label. In some occasions, we use other sensors to help benchmark, but we primarily try to use cameras for this system.
Okay, thanks.
Yeah, I mean, I think we want to aim for the car to be positioned accurately to the sort of centimeter level, something on that order.
Obviously, it will depend on distance. Like close by things can be much more accurate than farther away things, and they would matter less because the car doesn't have to make decisions much farther away. And as it comes close, it will become more and more accurate.
Exactly. A lot of questions.
Thanks, everybody. My question has to do with sort of AI and manufacturing. It's been a while since we've heard about the alien dreadnought concept. Is the humanoid that's behind you guys, is that kind of brought out of the production hell timeline and saying that humans are underrated in that process?
Well, sometimes like something that I say is taken to too much of an extreme. There are parts of the Tesla system that are almost completely automated. And then there are some parts that are almost completely manual. If you were to walk through the whole production system, you would see a very wide range from, like I said, fully automatic to almost completely manual. But the vast majority, most of it is already automated. And then with some of the design architecture changes, like going to large aluminum high-pressure die-cast components, we can take the entire rear third of the car and cast it as a single piece. And now we're going to do the front third of the car as a single piece. So the body line drops by like 60 to 70% in size. But yeah, the robot is not prompted by specifically by manufacturing needs. It's just that we're just obviously making the pieces that are needed for a useful humanoid robot. So I guess we probably should make it. And if we don't, someone else will. And so I guess we should make it and make sure it's safe. I should say, like, also manufacturing, volume manufacturing is extremely difficult and underrated, and we've gotten pretty good at that. It's also important for that humanoid robot. Like, how do you make the humanoid robot not be super expensive? And
Hi. Thank you for the presentation. And my question will be about scaling of Dojo. And in particular, how do you scale the compute nodes in terms of thermals and power delivery? Because there is only so much heat that you can dispense. and only so much power that you can bring to like cluster rack. And how do you plan to scale it, and how do you plan to scale it in multiple data centers?
Sure. You want to take it? Oh, there.
Yeah, hi. I'm Bill. I'm one of the Dojo engineers. So from a thermal standpoint and power standpoint, we've designed it very modular. So what you saw in the compute tile, that will cool the entire tile. So once we hook it up to, it is liquid cooled on both the top and the bottom side. It doesn't need anything else. And so when we talk about clicking these together, once we click it to power and once we click it to cooling, it will be fully powered and fully cooled. And all of that is less than a cubic foot.
Yeah, so Tesla has a lot of expertise in power electronics and in cooling. So we took the power electronics expertise from the vehicle powertrain and the sort of the advanced cooling that we developed for the power electronics and for the vehicle, and applied that to the supercomputer. Because as you point out, getting heat out is extremely important. It's just really heat limited. So, yeah, so it's funny that like at the compute level, it's operating at less than a volt, which is a very low voltage. There's a lot of amps, so therefore a lot of heat. I squared R is really bites you on the ass.
Hi, my question's also similarly a question of scaling. So it seems like a natural consequence of using, significantly faster training hardware is that you'd be either training models over a lot more data, or you'd be training a lot more complex models, which would be potentially significantly more expensive to run at inference time on the cars. I guess I was wondering, if there was a plan to also apply Dojo as something that you'd be using on the self-driving cars, and if so, do you foresee additional challenges there?
So as you could see, Andre's models are not just for cars. There are auto labeling models. There are other models that are beyond car application, but they feed into the car stack. So Dojo will be used for all of those too, not just the car inference part of the training.
Yeah, I mean, the Dojo's first application will be consuming video data for training that would then be run in the inference engine on the car. But, and that I think is an important test to see if it actually is good, but is it actually better than GPU cluster or not? But then beyond that, it's basically a generalized neural net training computer. But it's very much optimized to be a neural net. So, CPUs and GPUs, they're not made to be, they're not designed specifically for training neural nets. We've been able to make GPUs especially very efficient for training neural nets, but that was never their design intent. So it's basically, GPUs are still essentially running at neural net training in emulation mode. So with Dojo, we're saying okay, let's just ASIC the whole thing. Let's just have this thing it's built for one purpose, and that is neural net training. And just generally, any system that is designed for a specific purpose will be better than one that is designed for a general purpose.
Hey, I had a question here. Hi. So you described two separate systems. One was for vision, the other was for planner and control. Does Dojo allow you to train networks that cross that boundary? And second thing is, if you were able to train such networks, would you have the onboard compute capability in the FSD system to be able to run that under your tight latency constraints? Thanks.
Yeah, I think we should be able to train planner networks on Dojo or any GPUs. It's really invariant to the platform. And I think, if anything, once we make this entire thing end-to-end, it will be more efficient than decoding a lot of these intermediate states. So we should be able to run faster if we make the entire thing end-to-end neural networks. We can avoid a lot of decoding of these intermediate states and only decode the essential things required for driving the car.
Yep. Certainly, end-to-endness is the guiding principle behind a lot of the network developments. And over time in the stack, neural networks have taken on more and more functionality. And so we want everything to be trained end-to-end because we see that that works best. But we are building it incrementally. So right now, the interface, there is vector space, and we are consuming it in the planner, but nothing really fundamentally prevents you from actually taking features and eventually fine-tuning end-to-end. So I think that's definitely where this is headed.
And the discovery really is like, what are the right architectures that we need to place in the network blocks to make it amenable to that task? So like Andre described, we can place spatial RNNs to help with the perception problem. And now it's just neural network. So similarly for planning, we need to bake in search and optimization into the network architecture. And once we do that, you should be able to do planning very quickly, similar to C++ algorithms.
Oh, you don't, okay. I think I had a question very similar to what he was asking about. It seems like a lot of neural nets are around computer vision. And kind of traditional planning, you had model predictive control and solving convex optimization problems very quickly. And I'd wonder if there's a compute architecture that's more suited for convex optimization or the model predictive control solutions very quickly.
Yeah, 100%. We want to bake in, like I said earlier, we want to bake in these architectures that do, say, model predictive control, but it just like replace some of the blocks with neural networks. Or if we know the physics of it, we can also use physics-based models, part of the neural networks forward pass itself. So we are going to go towards a hybrid system where we will have neural network blocks placed together with physics-based blocks and more neural networks later. So it will be a hybrid stack, and what we know to do well, we place it explicitly, and what the networks are great at, we'll use the networks to optimize this. So build an end-to-end stack with this architecture baked in.
I mean, I do think that so as long as you've got like surround video neural nets for understanding what's going on and can convert the surround video into vector space, then you basically have a video game. And if it's like if you're in Grand Theft Auto or whatever, you can make the cars drive around and pedestrians walk around without crashing. So you can do. You don't have to have a neural net for control and planning, but it's probably ultimately better. But I think you can probably get to, in fact, I'm sure you can get to much safer than human with control and planning, primarily in C++ with perception, vision in neural nets.
Hi. My question is, we've seen other companies, for example, use reinforcement learning and machine learning to optimize power consumption in data centers and all kinds of other internal processes. My question is, is Tesla using machine learning within its manufacturing, design, or other engineering processes?
I discourage use of machine learning because it's really difficult. Unless you have to use machine learning, don't do it. It's usually a red flag when somebody says, we want to use machine learning to solve this task. I'm like, that sounds like bullshit. 99.9% of the time, you do not need it. So it's kind of like you reach for machine learning when you need to. No, but I've not found it to be a convenient, easy thing to do. It's a super hard thing to do. That may change if you've got a humanoid robot that can, understand normal instructions. Generally minimize use of machine learning in the factory.
Hi. Based on your videos from the simulator, it looked like a combination of graphical and neural approaches. I'm curious what the set of underlying techniques that are used for your simulator and specifically for neural rendering, if you can share.
Yeah, so we're doing, at the bottom of the stack, it's just traditional game techniques, just rasterization, real time, very similar to what you'd see in like GTA. On top of that, we're doing real-time ray tracing, and then those results were really hot off the press. We had that little asterisk at the bottom that was from last night. We're going into the neural rendering space. We're trying out a bunch of different things. We want to get to the point where the neural rendering is the the cherry on the top that pushes it to the point where the models will never be able to overfit on our simulator. Currently, we're doing things similar to photorealism enhancement. There's a recent paper enhancing photorealism enhancement, but we can do a lot more than what they could do in that paper because we have way more labeled data, way more compute, and also we have a lot more control over our environments. And we also have a lot of people who can help us make this run at real time. But we're going to try whatever we can do to get to the point where we can train everything just with the simulator if we had to, but we will never have to because we have so much real-world data that no one else has. It's just to fill in the little gaps in the real world.
Yeah, I mean, the simulator is very helpful when there's like these rare cases, like collision avoidance right before an accident. And then, ironically, the better our cars become at avoiding accidents, the fewer accidents there are, so then our training set is small, so then we have to make them crash in the simulation. So it's like, okay, minimize potential injury to pedestrians and people in the car. You have 5 meters, you're traveling at 20 meters per second. What actions would minimize probability of injury? We can run that in sim. So, cars driving down the wrong side of the highway, that kind of thing. Happens occasionally, but not that often.
For your humanoid context, I'm wondering if you've decided on what use cases you're going to start with and what the grand challenges are in that context to make this viable.
Well, I think for the Tesla bot, Optimus, it's basically going to start with just dealing with work that is boring, repetitive, and dangerous. Basically, what is the work that people would least like to do? Yeah.
Hi. So quick question about your simulations. Obviously, they're not perfect right now. So are you using any sort of domain adaptation techniques to basically bridge the gap between your simulated data and your actual real-world data? Because I imagine it's kind of dangerous to just deploy models which are solely trained on simulated data. So maybe some sort of explicit domain adaptation or something. Is that going on anywhere in your pipeline?
So currently, we're producing the videos straight out of the simulator, the full clips with kinematics and everything, and then we're just immediately training on them, but it's not the entire data set. It's just a small targeted segment, and we only are evaluating based on real-world video. We're paying a lot of attention to make sure we don't overfit, and if we have to start doing fancier things, we will, but currently we're not having an issue with it overfitting on the simulator. We will as we scale up the data, and that's what we're hoping to use neural rendering to bridge that gap, to push that even further out. We've already done things where we're using like the same network as in the car, but retrain it to detect sim versus real to drive our art decisions. And that's actually helped prevent some of these things as well.
Yeah, just to emphasize that overwhelmingly, the data set is the real video from the cars on the actual roads. Nothing's weirder or has more corner cases than reality. It gets really strange out there. But then if we find, say, a few examples of something very odd, and there's some very odd pictures we've seen, then in order to train it effectively, we want to create simulations, say 1,000 simulations that are variants of that quirky thing that we saw, to fill in some important gaps and make the system better. And really, all of this is about, over time, just reducing the probability of a crash or an injury, and it's called the march of nines. Like, how do you get to 99.9999999% safe? And each 9 is an order of magnitude difficulty increase.
Hey, all. Thanks so much for the presentation. I was curious about the Tesla bot. Specifically, I'm wondering if there are any specific applications that you think the humanoid form factor lends itself to. And then secondary, because of its human form factor, is emotion or companionship at all
thought about on the product roadmap at all?
Well, we certainly hope this does not feature in a dystopian sci-fi movie. But you know, like, really, at this point, we're saying like maybe this robot can we're trying to be as literal as possible. Can it do boring, dangerous, repetitive jobs that people don't want to do? And you know, once we can have it do that, then maybe it can do other things too. But that's the thing that would be really great to have. So it could be your buddy too. I mean, you can buy one and have it be your friend and whatever. I'm sure that people will think of some very creative uses.
So firstly, thanks for the really incredible presentation. My question is on the AI side. So one thing we've been seeing is that with some of these language modeling AIs, we've seen that scaling has just had incredible impacts in their capabilities and what they're able to do. So I was wondering whether you're seeing similar kinds of effects of scaling in your neural networks and your applications.
Absolutely. A bigger network, typically we see it performs better, provided you have the data to also train it with. And this is also what we see for ourselves. Definitely in the car, we have some latency consideration to be mindful of. And so there we have to get creative to actually deploy much, much larger networks. But as we mentioned, we don't only train neural networks for what goes in the car. We have these auto-labeling pipelines that can utilize models of arbitrary size. So in fact, we've trained a number of models that are not deployable, that are significantly larger and work much better because we want 100%, like we want much higher accuracy for the auto-labeling. And so we've done a lot of that, and there we definitely see this trend.
Yeah, the order labeling is an extremely important part of this whole situation. Without the order labeling, I think we would not be able to solve the self-driving problem.
It's kind of a funny form of distillation where you're using these very massive models plus the structure of the problem to do this reconstruction, and then you distill that into neural networks that you deploy to the car. But we basically have a lot of neural networks and a lot of tasks that are never intended to go into the car.
Yeah, and also as time goes on, there you get new frames of information. So you really want to make sure your computer is distributed across all the information as opposed to just taking a single frame and hogging on it for, say, 200 milliseconds. You actually want to have newer frames coming in. So you want to like use all of the information and not just use that one frame.
I think one of the things we're seeing is that the car's predictive ability is eerily good. It's really getting better than human in terms of predicting, like you said, like predict what this road will look like when it's out of sight, like it's around the bend, and it predicts the road with very high accuracy, you know, predict pedestrians or cyclists where behind, you know, where it just sees a little corner of the bicycle and a little bit through the windows of the bus. And its ability to predict things is going to be much better than humans, like really way beyond.
Right. Yeah, we see this often where we have something that is not visible, but the neural network is making up stuff that actually is very sensible. Sometimes it's eerily good, and you have to like, you're wondering this is in the training set. And actually in the limit, you can imagine the neural net has enough parameters to potentially remember Earth. So in the limit, it could actually give you the correct answer, and it's kind of like an HD map baked into the weights of the neural net.
Yeah.
I have a question about the design of the Tesla bot. Specifically, how important is it to maintain that humanoid form? To build hands with 5 fingers that also respects the weight limits could be quite challenging. You might have to use cable-driven, and then that also causes all kinds of issues.
I mean, this is just going to be bot version 1. I mean, we'll see. So it needs to be able to do things that people do, and you know, be a generalized kind of humanoid robot. I mean, you could potentially have it give it like, you know, 2 fingers and a thumb or something like that. You know, for now we'll give it 5 fingers and see if that works out okay. It probably will. It doesn't need to be like you know, have like incredible grip strength. but it needs to be able to work with tools, so, and carry a bag, that kind of thing.
Hi, thanks a lot for the presentation. So an old professor of mine told me that the thing he disliked a lot about his Tesla was that the autopilot UX didn't really inspire much confidence in the system, especially when like objects are spinning, classifications are flickering. I was wondering, even if you have a good self-driving system, how are you working on convincing Tesla owners, other road users and just the general public that your system is safe and reliable?
Well, I think that's the cars. A while back, cars used to spin. They don't spin anymore. Not in. If you've seen the FSD beta videos, they're pretty solid, and they will be getting more solid.
Yeah, as you add more and more data and train these multi-cam area networks, like these are pretty recent, actually, just like a few months old, and it's still improving. It's not a done product, and in our minds we can clearly see how this is just going to be like perfect vector space, because why not? All the information is there in the videos. It should produce it given lots of data and good architectures. And this is just an intermediate point in that timeline.
I mean, it's clearly headed to way better than human, without question.
My turn? Oh, hi, here. I was wondering if you could talk a little bit about the short to medium-term economics of the bot. I guess I understand the long-term vision of replacing physical labor, but I also think repetitive, dangerous, and boring tasks tend to not be so highly compensated. And so I just don't see how to reproduce the, start with a supercar and then break into like the lower end of the market. How do you do that for a robot humanoid?
Well, I guess you'll just have to see.
Hello. Hi. I was curious to know how the car AI prioritizes occupant safety versus pedestrian safety, and what thought process goes into like deciding how to bake this into the AI.
Well, I mean, the thing to appreciate is that from the computer standpoint, everything is moving slowly. So to a human, things are moving fast. To the computer, they are not moving fast. So I think this is, in reality, somewhat of a false dichotomy. Not that it will never happen, but it will be very rare. If you think of it like, going the other direction, like rendering, with full ray tracing, neural net enhanced graphics on something like Cyberpunk or any advanced video game, doing 60 frames a second, perfectly rendered. Like, how long would it take a person to even render one frame, and without any mistakes? Can't be done. I mean, it would take like a month just to render one frame out of 60 in a second in a video game. It's computers are fast and humans are slow. I mean, for example, on the rocket side, you cannot steer the rocket to orbit. We actually hooked up a joystick to see if anyone could steer the rocket to orbit, but you need to react at roughly 6-7 hertz. People can't do it. Not even that's pretty low. We're talking more like aiming for like 30 hertz type of thing.
Hi, over here, with hardware 3, there's been lots of speculation that with larger nets, it's hitting the limits of what it can provide. How much headroom has the extended compute modes provided, and at what point would hardware 4 be required, if at all?
Well, I'm confident that hardware 3 or the full self-driving computer 1 will be able to achieve full self-driving at a safety level much greater than a human, probably, I don't know, at least 200 or 300% better than a human. Then obviously there will be a future hardware 4 or full self-driving computer 2, which we'll probably introduce with the Cybertruck, so maybe in about a year or so. That is probably, well, that'll be about 4 times more capable, roughly. But it's really just going to be like, can we take it from, say, for argument's sake, 300% safer than a person to 1,000% safer? Just like there are people on the road who, with varying driving abilities, but we still let people drive. You don't have to be the world's best driver to be on the road. So as we see, so yeah. You guys want to say anything? All right.
So are you worried at all, since you don't have any depth sensors on the car, that people might try like adversarial attacks, like printed out photos or something to try to trick the RGB neural network?
Yeah, like what? Pull some like Wile E. Coyote stuff, like paint the tunnel on the wall. It's like, oops. We haven't really seen much of that. I mean, for sure, like right now, if you, most likely, if you had like a T-shirt with a T-shirt with like a stop sign on it, which I actually have a T-shirt with a stop sign on it, and then you like flash the car, it will stop. I proved that. But we can obviously, as we see these adversarial attacks, then we can train the cars to, notice that, well, it's actually a person wearing a T-shirt with a stop sign on it, so it's probably not a real stop sign. Yeah.
Hi, my question is about the prediction and the planning. I'm curious, how do you incorporate uncertainty into your planning algorithms? Do you just basically assume, you mentioned that you run the autopilot for all of the other cars on the road. Do you assume that they're all going to follow those rules, or are you accounting for the possibility that, well, they might be bad drivers, for example?
Yeah, we do account for multimodal futures. It's not that we just choose one. We account for, okay, this person can actually do many things. And we use their actual physics and kinematics to make sure that they're not doing a thing that would interfere with us before we act. So if there's any uncertainty, we are conservative and then would yield to them. Of course, there's a limit to this, because if you're too conservative, then it's probably not practical. So at some point, we have to assert. And even then, we make sure that the other person can yield to us and act sensibly.
I should say, before we introduce something into the fleet, we will run it in shadow mode, and we'll see what would this neural net, for example, have done in this particular situation, and then effectively the drivers are training the net. So if the neural net would have controlled and say veered right, but the person actually went left, and it's like, oh, there was a difference. Why was there that difference?
Yeah, and secondly, we also...
All the human drivers are essentially training the neural net as to what is the correct course of action, assuming it doesn't then end up in a crash. It doesn't count in that case.
Yeah, and secondly, we have various estimates of uncertainty like flicker, and when we observe this, we actually say if you're not able to see something, we actually slow down the car to be, again, safe and get more information before acting. Yeah, we don't want to be brazen and just go into something that we don't know about. We only go into places where we know about.
Yeah, yeah. It should be like, aspirationally, the car should be the less it knows, the slower it goes.
Yeah.
This is
not true at some point, but now it's
improving. Should be speed proportionate to confidence.
Thanks for the presentation. So I am curious, appreciate the fact that the FSD is improving, but if you have the ability to improve one component along the AI stack that presented today, whether it is simulation, data collections, planning and control, etc., which one, in your opinion, is going to have the biggest impact for the performance of the full self-driving system?
It's really the area under the curve of these multiple points, and if you improve anything, it should improve the area.
I mean, the short term, it's arguably we need all of the nets to be surround video, And so we still have some legacy. This is very short term. Obviously, we're fixing it fast. But there's still some nets that are not using surround video. And I think ideally they'd all use surround video. Yeah. Maybe. Yeah.
I think a lot of puzzle pieces are there for success. We just need more strong people to also just help us make it work.
Yeah, that is the actual bottleneck.
So that is the actual bottleneck, I would say, and really one of the reasons that we are putting on this event.
Exactly. Well said, Andre. That there's just a tremendous amount of work to do to make it work. So that's why we need talented people to join and solve the problem.
Thank you for the great presentation. Lots of my questions answered. But one thing is, when imagine that now you have a large amount of data, even unnecessary. How do you consider that? Like there is a forgetting problem in neural networks. Like how are you considering those aspects? And also another one, are you considering an online learning or continuous learning, so that maybe each driver can have their version of self-driving software?
I think I know the literature that you're referring to. That's not some of the problems that we've seen, and we haven't done too much continuous learning. We trained the system once, we fine-tuned a few times. That sort of goes into the car. We need something stable that we can evaluate extensively, and then we think that that's good, and that goes into cars. So we don't do too much learning on spot or continuous learning, and don't face the forgetting problem.
But there will be settings that you can say, like, if you are you typically a conservative driver, or do you want to drive fast or slow? You know, it's like I'm late for the airport. Could you go faster than, basically the kind of instructions you'd give to your Uber driver. It's like I'm late for the flight, please hurry, or take it easy, or whatever your style is. So let's take a few more questions here. And then we'll call it a day.
All right. So as our models have become more and more capable, and I guess you're deploying these models into the real world, one thing I guess that's possible is for AI to become more, I guess, misaligned with what humans desire. So I guess, is that something that you guys are worried about as you guys deploy more and more robots? Or do you guys, we'll solve that problem when we get there?
Yeah, I think that we should be worried about AI. Now, what we're trying to do here is, say, narrow AI, pretty narrow, like just make the car drive better than a human. And then have the humanoid robot be able to do basic stuff. At the point at which you sort of start to get to superhuman intelligence, I don't know, all bets are off. But and that'll probably happen. But what we're trying to do here at Tesla is make useful AI that people love and is unequivocally good. That's our, we'll try to aim for that. Okay, maybe one more question.
Hi, my question is about the camera sensor. In the beginning of the talk, you had mentioned about building a synthetic animal. And if you think about it, a camera is a very poor approximation of a human eye. And a human eye does a lot more than take a sequence of frames. Have you looked into, there are these days are cameras like event cameras. Have you looked into them? Or are you looking into a more flexible camera design or building your own camera, for example?
Well, with Hardware 4, we will have a next generation camera. But I have to say that the current cameras, we have not reached the limit of the current cameras. And I'm confident we can achieve full self-driving with much higher safety than humans with the current cameras and current compute hardware. But it would be good to be 1,000% better rather than 300% better. So we'll see continued evolution on all levels in pursuit of that goal. And I think in the future, people will look back and say, wow, I can't believe we had to drive these cars ourselves. It'll like self-driving cars will just be just a normal, like self-driving elevators. Elevators used to have elevator operators. And there's someone there with a big relay switch operating the elevator. And then every now and then they'd get tired or make a mistake and shear somebody in half. So, so now we made elevators automatic, and you just go and you press the button, and you can be in a 100-story skyscraper and don't really worry about it. Just go in and press the button, and the elevator takes you where you want to go. But it used to be that all elevators were operated manually. And it'll be the same thing like for cars. All cars will be automatic. And then, and electric, obviously. So there will still be some gasoline cars and some manual cars, just like there are still some horses. So, all right, well, thanks everyone for coming, and hope you enjoyed the presentation, and thank you for the great questions. All right.